Welcome back to Scientific Discovery Hub, where we explore the universe's most mind-bending mysteries. Today, we're diving into a cosmic enigma that's turning cometary science on its head. 3I Atlas, the third interstellar object ever discovered to visit our solar system. Picture a speeding comet, zipping through space at 58 kilometers per second, carrying secrets from a distant star system, and defying everything we thought we knew about comets. That's 3I Atlas, and its story is about to blow your mind. Discovered by the Atlas survey, this interstellar traveler isn't your average icy snowball. While most comets in our solar system are rich in water, 3I Atlas spews 8 times more carbon dioxide than water vapor, a bizarre chemical signature that's shaking up models of how comets form and evolve. How does a cosmic wanderer from another star system end up with such an alien recipe? And what does this mean for our understanding of planetary systems across the galaxy? In this video, we'll unpack the hyperbolic highway of 3I Atlas's mind-blowing trajectory, peel back the layers of its icy nucleus, and decode its CO₂-rich Coma and tail. We'll compare it to its interstellar siblings, Oumuamua and Borisov, and even explore the wild debate about whether it could be an alien artifact. Spoiler, science says no, probably. Along the way, we'll tackle big questions. Could 3I Atlas be a 7 billion-year-old relic from the Milky Way's past? How do stellar encounters shape its journey? And why can't we launch a probe to catch up with it? Whether you're a space enthusiast or new to astrophysics, this video will take you on a journey from the comet's fiery arrival to its implications for the future of interstellar exploration. So hit play, buckle up, and join us as we unravel how 3I Atlas is rewriting the rules of cometary science, one molecule of carbon dioxide at a time. Don't forget to like, subscribe, and ring the bell for more deep dives into the wonders of the cosmos. Let's explore the universe together. In the vast tapestry of the cosmos, where stars burn in silent grandeur and planets trace ancient orbits, the arrival of a stranger is always a moment of profound significance. Such is the case with 3I Atlas, the third interstellar object ever discovered to have ventured into our solar system. Unlike the countless comets and asteroids born from the remnants of our own stellar cradle, this interloper hails from another star system, carrying with it the whispers of a distant world. Its discovery on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, marked not just a scientific breakthrough, but a philosophical shift in humanity's perception of its place in the universe. 3I Atlas is not merely a passing celestial body. It is a messenger from the depths of interstellar space, bearing clues about the origins of planetary systems beyond our own. The comet's journey is one of velocity and defiance of gravity. Entering the inner solar system at a staggering 58 kilometers per second, 3I Atlas follows a hyperbolic trajectory that proves its origin lies outside the sun's gravitational embrace. This speed alone sets it apart from the comets and asteroids that originate from the Oort cloud or the Kuiper belt, whose paths are bound by the sun's pull. Instead, 3I Atlas is on a one-way voyage, destined to escape the solar system after its brief encounter. Its path, meticulously tracked by observatories across the globe, reveals an orbital eccentricity of 6.1414, an indication that it is not a transient visitor from the outer reaches of our system, but a traveler from another corner of the galaxy. The discovery of 3I Atlas is a testament to the power of modern astronomical surveys, blending ancient human curiosity with cutting-edge technology to unveil the hidden secrets of the cosmos. Yet the true fascination with 3I Atlas lies not only in its trajectory, but in the composition of its icy heart. Early observations revealed a coma, a cloud of gas and dust surrounding its nucleus that glows with a reddish hue, a signature of complex organic molecules and irradiated compounds. Spectroscopic analysis conducted by the James Webb Space Telescope and the Hubble Space Telescope unveiled a startling revelation. 3I Atlas is rich in carbon dioxide, a substance far less abundant in native solar system comets. This anomaly raises profound questions about the conditions under which the comet formed. Did it arise in a protoplanetary disk, where carbon dioxide condensed into ice at great distances from its parent star? Or is this a reflection of a different chemical equilibrium in an alien stellar neighborhood? The answers lie buried within the comet's nucleus, waiting to be unraveled by the tools of modern astronomy. As 3I Atlas continues its journey, its significance transcends the realm of pure science. It serves as a reminder that the universe is not a static expanse, but a dynamic, interconnected web of celestial bodies in constant motion. The comet's arrival challenges our assumptions about the rarity of interstellar visitors and compels us to reconsider the frequency with which such objects might cross our cosmic path. More than that, it invites us to ponder the possibility that the building blocks of life, the elements that form planets and moons, may be shared across the galaxy, carried by these nomadic wanderers. In the quiet glow of its coma, 3I Atlas whispers of a universe teeming with stories yet to be told. And it is our duty to listen. The path of 3I Atlas is a testament to the sheer scale of the cosmos and the forces that govern motion within it. As it hurtles through the inner solar system, the comet follows a trajectory so extreme that it defies the gravitational grasp of the Sun. Its hyperbolic path is defined by an orbital eccentricity of 6.1414, a number so far removed from the elliptical orbits of planets and native comets that it speaks of an origin beyond the boundaries of our own system. This eccentricity is the result of the comet's immense speed, 58 kilometers per second, as it enters the solar system. To put this into perspective, the previous interstellar visitors, 1I Oumuamua and 2I Borisov, had hyperbolic excess velocities of 26 and 32 kilometers per second, respectively. 3I Atlas, however, is moving nearly twice as fast as Oumuamua and almost 80% faster than Borisov, a fact that underscores the comet's extraordinary nature. The mechanics of 3I Atlas's journey are governed by the laws of celestial dynamics, yet its existence challenges our understanding of how such objects are distributed throughout the galaxy. The comet's trajectory brings it to a closest approach of 1.36 astronomical units, AU, from the Sun, placing it between the orbits of Earth and Mars. At this distance, the Sun's gravity accelerates the comet to its maximum velocity of 68 kilometers per second. Yet, despite this acceleration, 3I Atlas will not be captured by the solar system. Instead, it will continue its outward journey, propelled by the kinetic energy it carried from its birthplace. This behavior is characteristic of interstellar objects, which possess the necessary velocity to escape the gravitational influence of the Sun entirely. The fact that 3I Atlas is not perturbed significantly by the planets further confirms its interstellar origin. While gravitational interactions with massive bodies like Jupiter could alter the trajectory of a native solar system object, such influences are negligible here, reinforcing the conclusion that 3I Atlas is a visitor from another star system. The discovery of 3I Atlas by the Atlas survey is a remarkable feat of modern astronomy, achieved through a combination of automated observation systems and dedicated human effort. The comet was first detected on 1 July 2025 at an apparent magnitude of 18, meaning it is only visible with powerful telescopes. At the time of discovery, it was located 4.51 AU from the Sun, already deep within the inner solar system, but still distant enough that its interstellar nature was not immediately apparent. Follow-up observations from the Zwicky Transient Facility, ZTF, the Very Large Telescope, VLT, and the newly commissioned Vera C. Rubin Observatory played a crucial role in refining the comet's orbit and confirming its hyperbolic path. These observations revealed that 3I Atlas had passed through the dense star fields near the galactic center as early as 21 May 2025, a location that made it difficult to distinguish from the myriad of background stars. The comet's discovery is a testament to the growing capabilities of wide-field sky surveys, which are increasingly capable of detecting faint and fast-moving objects in the night sky. What makes 3I Atlas particularly intriguing is its alignment with the ecliptic, the plane in which the planets orbit the Sun. Unlike the previous interstellar object, 1I Oumuamua, which approached from a direction nearly perpendicular to the ecliptic, 3I Atlas arrives from the southern celestial hemisphere, a direction that had not been strongly predicted by earlier models of interstellar object distribution. This unexpected origin challenges assumptions about the likelihood of detecting interstellar objects from different parts of the sky. While astronomers had theorized that interstellar objects would predominantly come from the solar apex, the direction in which the Sun is moving through the galaxy, 3i Atlas's trajectory suggests that such objects may arrive from a variety of angles, influenced by the complex gravitational interactions within the Milky Way. The comet's retrograde motion, with an inclination of 5° relative to the ecliptic, further complicates its story, hinting at a past encounter with a massive body in its home system, or a chance collision that sent it on its interstellar voyage. As 3i Atlas continues its journey, it will pass relatively close to several planets, though none pose a threat to Earth. On 3 October 2025, it will come within 0.19 AU of Mars, a distance close enough that orbiters around the red planet may have the opportunity to observe the comet in unprecedented detail. Following its perihelion passage on 29 October 2025, the comet will pass 0.65 AU from Venus on 3 November 2025. However, its closest approach to Jupiter will occur on 16 March 2026, when it will pass within 0.36 AU of the gas giant. These planetary encounters provide valuable opportunities for further study, as the gravitational influence of these massive worlds may subtly alter the comet's trajectory. Yet, given its immense speed and the relatively small mass of the planets compared to the comet's kinetic energy, the effect on 3i Atlas's path will be minimal. The comet's fate is clear. It will depart the solar system as swiftly as it arrived, carrying with it the mysteries of its origin. As it recedes into the abyss of interstellar space, the observations gathered during its brief visit will serve as a window into the distant star system from which it came. The study of 3i Atlas is not merely an exercise in cataloging another celestial body. It is a step toward understanding the broader architecture of the galaxy and the processes that shape the formation of planetary systems. Through continued observation and analysis, scientists hope to unravel the enigma of this interstellar traveler and gain insight into the countless other objects that may one day cross our cosmic path. The study of 3i Atlas is more than an academic pursuit. It is a profound exploration of the fundamental processes that govern the formation and evolution of planetary systems. As the third confirmed interstellar object to visit our solar system, 3i Atlas presents a unique opportunity to compare the chemical and structural characteristics of a comet from an alien star system with those of native comets. The insights gleaned from this comparison could reshape our understanding of how planets and their satellites coalesce, offering a glimpse into the diverse conditions that exist in other corners of the galaxy. The comet's unusual composition, particularly its high abundance of carbon dioxide, stands out as a compelling anomaly that challenges established models of cometary formation and evolution. In solar system comets, carbon dioxide is present in much lower quantities, typically sublimating at greater distances from the Sun compared to water ice. The fact that 3i Atlas retains such a high proportion of CO2, even at a distance of 3.32 AU from the Sun, suggests that it may have formed in a region where temperatures were sufficiently low for CO2 to condense into ice. This implies that the comet may have originated in a protoplanetary disk, with a distinct thermal and chemical profile, possibly one that was influenced by a different stellar environment or evolutionary history. Understanding the mechanisms that led to such a composition could provide critical clues about the conditions under which planets and their accompanying debris form in other star systems. Moreover, the detection of water ice, water vapor, carbon monoxide, and carbonyl sulfide in 3i Atlas's Coma adds another layer of complexity to its story. The presence of water ice is particularly significant, as it is a key ingredient for the development of life and plays a central role in shaping the surfaces and atmospheres of planetary bodies. The fact that 3i Atlas carries water ice in a form that is likely amorphous, distinct from the crystalline ice found in solar system comets, suggests that the comet may have experienced a different history of heating and irradiation. Amorphous ice forms under conditions of rapid cooling, implying that 3i Atlas may have spent a considerable portion of its journey in a region of the galaxy where temperatures remained low enough to prevent the restructuring of its ice into a crystalline lattice. This finding has profound implications for our understanding of the distribution of volatiles in the galaxy. and the potential for water to be transported between star systems. If comets like 3I Atlas can carry water and other essential compounds across interstellar space, it raises the tantalizing possibility that the building blocks of life are more widespread than previously imagined. Beyond its chemical composition, the physical characteristics of 3I Atlas offer valuable insights into the processes that shape cometary nuclei. The comet's nucleus, estimated to be between 0.32 and 5.6 kilometers in diameter, is shrouded in a coma of gas and dust that obscures direct observations. However, the data obtained from the Hubble Space Telescope and the James Webb Space Telescope suggest that the nucleus is relatively small, likely less than 1 kilometer in diameter. This is consistent with the behavior of other comets, which tend to be fragile and loosely consolidated aggregates of ice, dust, and rock. The fact that 3I Atlas is actively outgassing at a distance of over 4 AU from the Sun indicates that it possesses a high concentration of volatile ices that can sublimate even at relatively low temperatures. This property may be a consequence of its interstellar origin, where such ices could have been preserved in a more pristine state due to the absence of the intense radiation and gravitational perturbations that characterize the inner regions of planetary systems. The study of 3I Atlas's nucleus and coma provides a rare opportunity to examine the internal structure of a comet that has not been subjected to the same environmental pressures as those in the solar system, shedding light on the diversity of cometary bodies that may exist throughout the galaxy. The trajectory of 3I Atlas also holds important clues about its origins and the history of its journey through the Milky Way. The comet's hyperbolic excess velocity of 58 kilometers per second is the fastest recorded for an interstellar object, suggesting that it has not been significantly slowed by gravitational interactions with other stars or massive bodies in its vicinity. This high velocity implies that 3I Atlas may have been ejected from its home system with considerable force, possibly due to a close encounter with a giant planet or a binary companion star. Such ejection mechanisms are well documented in simulations of planetary system formation, where gravitational interactions between large planets and smaller bodies can result in the expulsion of comets and asteroids into interstellar space. The fact that 3I Atlas has retained such a high velocity over billions of years of travel reinforces the idea that it is a relatively recent ejection from its parent system rather than a remnant from an earlier era of galactic history. Furthermore, the comet's retrograde motion and inclination relative to the ecliptic suggest that it may have originated in a different region of the galaxy, potentially in a stellar population that is dynamically distinct from the stars in our immediate vicinity. By tracing the comet's trajectory backward in time, astronomers may be able to identify candidate stars that could have hosted 3I Atlas before its journey to the solar system, providing a rare glimpse into the long-lost history of a distant planetary system. Perhaps the most profound implication of 3I Atlas's discovery is the realization that interstellar objects may be more common than previously assumed. The detection of a third interstellar comet in less than a decade is a strong indication that such objects are not rare anomalies, but rather a natural consequence of planetary system evolution. This has significant consequences for our understanding of the galactic ecosystem, as it suggests that the exchange of material between star systems is an ongoing process. If comets like 3I Atlas routinely traverse the galaxy, they may play a role in distributing organic compounds, water, and other essential ingredients for life across vast cosmic distances. This idea aligns with the theory of panspermia, which posits that life or its precursors may be seeded from one planetary system to another through the transport of cometary and asteroidal material. While the direct transfer of biological organisms remains speculative, the movement of organic molecules between star systems is a well-supported concept in astrobiology. The study of 3I Atlas and other interstellar objects could therefore provide empirical evidence for the mechanisms that facilitate the spread of life's building blocks throughout the galaxy. In addition to its scientific value, 3I Atlas also serves as a humbling reminder of the vastness of the cosmos and the limitations of human knowledge. Despite the incredible technological advances that have enabled us to track and analyze this interstellar visitor, much about its origin and history remains shrouded in mystery. The comet's parent star, for instance, remains unidentified, as the vast timescale of its journey has erased any direct connection between the comet and its place of birth. The fact that 3I Atlas may be older than the solar system itself, potentially dating back 7 to 14 billion years, adds another layer of intrigue to its story, raising the possibility that it has witnessed the formation and destruction of entire planetary systems. This realization underscores the importance of continued investment in observational astronomy and the development of next-generation telescopes, which will be essential for uncovering the secrets of interstellar objects and expanding our understanding of the universe. As 3I Atlas continues its journey beyond the reach of our telescopes, the data collected during its brief visit will serve as a foundation for future research. The study of this interstellar comet is not merely an exercise in cataloging a rare celestial event. It is a step toward answering some of the most profound questions in science. What conditions prevail in other star systems? How do planetary systems evolve over time? And what role do interstellar objects play in shaping the distribution of matter across the galaxy? The answers to these questions lie hidden within the icy heart of 3I Atlas, waiting to be deciphered by the next generation of astronomers. The study of 3I Atlas is not merely an isolated scientific endeavor. It is the beginning of a new chapter in our understanding of the cosmos. As the third interstellar object to be discovered in less than a decade, it marks a turning point in our ability to observe and analyze celestial bodies that originate beyond our solar system. With each new interstellar visitor, we refine our techniques, enhance our instrumentation, and deepen our comprehension of the processes that shape planetary systems across the galaxy. The insights gained from 3I Atlas will inform future missions and observational strategies, guiding us toward a more comprehensive picture of the universe. The development of next-generation telescopes, such as the Vera C. Rubin Observatory and the James Webb Space Telescope, has already proven instrumental in tracking and characterizing interstellar objects, and their continued operation promises to reveal even more about these elusive travelers. As we improve our ability to detect and study interstellar comets and asteroids, we inch closer to answering fundamental questions about the origins of planetary systems, the distribution of organic materials, and the potential for life beyond Earth. Beyond the scientific implications, the discovery of 3I Atlas reminds us of the vast, interconnected nature of the cosmos. The comet's journey through interstellar space is a testament to the dynamic processes that govern the formation and evolution of planetary systems. Just as planets and moons are shaped by gravitational interactions and collisions, so too are comets and asteroids dispersed and propelled across the galaxy. The fact that 3I Atlas may have been ejected from its home system billions of years ago underscores the notion that planetary systems are not static entities, but rather evolving landscapes of celestial bodies in constant motion. The study of interstellar objects allows us to witness the long-term consequences of these cosmic interactions, offering a unique vantage point from which to observe the history of the galaxy. The realization that such objects may be far more common than once believed opens the door to new possibilities in planetary science, including the potential for interstellar material to influence the development of planetary systems and the emergence of life. As we look to the future, the search for interstellar objects will continue to push the boundaries of our observational capabilities. The upcoming launch of space-based observatories and the expansion of ground-based sky surveys will significantly enhance our ability to detect and track interstellar visitors. These advancements will not only improve our chances of identifying more interstellar objects, but also allow for more detailed characterization of their physical and chemical properties. The ability to conduct in-depth spectroscopic analyses of interstellar comets and asteroids will provide critical information about their compositions, helping us determine whether they originate from different types of star systems or regions within the galaxy. Additionally, the development of autonomous robotic missions capable of intercepting and studying interstellar objects up close could revolutionize our understanding of these celestial wanderers. While current technological limitations make such missions challenging, the lessons learned from tracking 3I Atlas and other interstellar objects will pave the way for future explorations that may one day enable us to retrieve samples from these distant visitors. The study of interstellar objects is not solely the domain of professional astronomers. It is a field that invites participation from enthusiasts, students, and researchers around the world. The contributions of amateur astronomers and citizen scientists have been vital in the discovery and monitoring of interstellar objects, like 3I Atlas. Their efforts, combined with the data from professional observatories, create a global network of observers working together to unravel the mysteries of the cosmos. As technology becomes more accessible and data-sharing platforms expand, the role of the broader community in interstellar astronomy will only grow. This collaborative spirit mirrors the very nature of the universe itself, interconnected, dynamic, and ever-expanding. The study of 3I Atlas is not just about understanding a single comet. It is about embracing the collective human endeavor to explore the unknown and seek answers to the most profound questions about our place in the universe. With each new interstellar object that enters our solar system, we gain another piece of the cosmic puzzle. 3I Atlas is but one of many such visitors that will shape our understanding of the galaxy in the decades to come. As we continue to refine our methods and expand our observational reach, we move closer to a future where interstellar objects are not mere curiosities, but integral components of our cosmic inventory. The study of these objects will not only deepen our knowledge of planetary formation and evolution, but also inspire new generations of scientists, engineers, and dreamers who will carry the torch of discovery forward. The universe is vast, and its secrets are waiting to be uncovered, one interstellar comet at a time. In the vast tapestry of the cosmos, where stars blaze like distant fires and galaxies spiral in silent majesty, a lone traveler has crossed the threshold of our solar system. Discovered in the summer of 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, 3I Atlas is a comet unlike any other, a celestial wanderer born not here, but in the far reaches of interstellar space. Its arrival marks a pivotal moment in human history, offering a glimpse into the primordial materials and processes that shaped worlds beyond our own. As it hurtles through the inner solar system on a hyperbolic trajectory, 3I Atlas carries with it the echoes of a star system long lost to time, a relic of a cosmic epoch predating the birth of the Sun itself. This comet, now designated 3I Atlas CC 2025 N1, is the third confirmed interstellar object to have graced our neighborhood, following the enigmatic 1I Oumuamua in 2017 and the more recently discovered 2I Borisov in 2019. Yet, 3I Atlas stands apart in its peculiarities. Its journey through the solar system is swift and unyielding, moving at a blistering 58 kilometers per second relative to the Sun, far exceeding the escape velocity of our stellar system. Unlike its predecessors, which offered fleeting glimpses before vanishing into the void, 3I Atlas lingers just long enough for humanity to unravel its mysteries. Through the lenses of the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories scattered across the globe, scientists have begun to decode the comet's origins, composition, and the forces that propelled it on its interstellar voyage. But 3I Atlas is more than a scientific curiosity. It is a bridge between the familiar and the unknown, a testament to the dynamic, interconnected nature of the universe. Its arrival stirs profound questions. Where did it come from? What ancient star system birthed it? And what secrets does it carry about the chaotic dance of matter in the Milky Way? As we peer into the heart of this interstellar wanderer, we are reminded of our place in the cosmos, not as isolated observers, but as participants in a grand unfolding story written in the language of stars. To understand 3I Atlas is to unravel the intricate machinery of a comet, an object forged in the cold depths of space, sculpted by the gravitational tides of distant stars and animated by the radiant energy of the Sun. At its core lies a nucleus, a frozen heart of rock, ice, and organic compounds, shrouded in a veil of gas and dust known as the Coma. This coma, glowing faintly in the light of the Sun, is a dynamic cloud of sublimated volatiles and ejected particles, a fleeting halo that reveals the comet's inner workings. The nucleus itself remains elusive, its true dimensions obscured by the haze of its own creation. Yet, through meticulous observation, scientists have begun to sketch its profile, a body no larger than a kilometer in diameter, yet potent enough to stir the heavens. The Sun, ever the architect of change, plays a central role in awakening Three-Eye Atlas. As the comet draws closer to our star, solar radiation penetrates its icy exterior, triggering a transformation akin to a thawing glacier. Volatile ices, primarily water, carbon dioxide, and carbon monoxide sublime into gas, erupting from the nucleus in violent jets. These eruptions lift dust from the surface, scattering it into space to form the Coma's sprawling expanse. The process is both delicate and destructive. The very forces that animate the comet also erode its structure, sculpting a surface pockmarked with vents and fractures. Observations by the Hubble Space Telescope in July 2025 revealed a coma spanning tens of thousands of kilometers, its reddish hue betraying the presence of complex organic molecules and irradiated carbon-rich grains. What sets Three-Eye Atlas apart from the comets of our own solar system is the abundance of carbon dioxide in its coma. The James Webb Space Telescope, with its unparalleled sensitivity to infrared light, detected CO₂ emissions at levels far exceeding those of typical comets, suggesting a nucleus rich in this molecule. Such a composition implies that Three-Eye Atlas formed in the frigid outer reaches of its parent star system, beyond the CO₂ frost line, where temperatures are low enough for this gas to freeze into solid form. Yet the comet's journey did not end there. Gravitational interactions, perhaps with a massive planet or a passing star, propelled it outward, hurling it into the interstellar void. The coma of Three-Eye Atlas is not static. It evolves with time, responding to the Sun's inexorable pull. By August 2025, the Very Large Telescope, VLT, had identified traces of cyanide gas and atomic nickel vapor, substances rarely observed in cometary tales. These elements, forged in the crucibles of ancient stars, hint at the comet's cosmic heritage. The detection of nickel in particular raises intriguing questions. How does such a heavy element survive the rigors of interstellar travel? Is its presence a remnant of a star's explosive death, or does it stem from the comet's own internal chemistry? These discoveries underscore the comet's role as a cosmic time capsule, preserving the fingerprints of a distant stellar nursery. Yet for all its complexity, Three-Eye Atlas remains a fragile entity. Its nucleus, though resilient, is vulnerable to the Sun's growing intensity. As the comet approaches perihelion on 29 October 2025, its activity will reach a crescendo, with jets of gas and dust painting the night skies of Mars in a ghostly glow. Whether it will endure this fiery encounter or fragment under the strain remains uncertain. But even if it disintegrates, Three-Eye Atlas's legacy will endure in the data it leaves behind, a testament to the enduring curiosity of humankind. The discovery of Three-Eye Atlas was not a singular event, but a confluence of vigilance, technology, and serendipity. On 1 July 2025, the Atlas Survey Telescope at Rio Hurtado, Chile, captured the first image of the comet at an apparent magnitude of 18, a faint smudge against the backdrop of the Milky Way. At the time, the object was already 4.5 astronomical units, AU, from the Sun, hurtling inward at a velocity of 61 kilometers per second. Initial observations raised alarms. Its trajectory suggested a close approach to Earth's orbit, prompting the Minor Planet Center to list it on the Near-Earth Object Confirmation page. Yet, as more data trickled in, the truth emerged. The comet was not a threat, but a visitor from interstellar space. The confirmation of Three-Eye Atlas's interstellar origin hinged on a global network of observatories, both professional and amateur. The Zwicky Transient Facility, ZTF, in California, and the Nordic Optical Telescope in the Canary Islands provided critical pre-discovery images, tracing the comet's path back to May 2025. Amateurs, too, played a role. Sam Dean, a dedicated observer, noted that Three-Eye Atlas had been obscured by the dense star fields near the galactic center, explaining why it evaded detection for weeks. By late July, the comet's identity was settled, a hyperbolic trajectory with an eccentricity of 6.14, the highest recorded for an interstellar object. confirmed that 3I Atlas had arrived from the depths of the galaxy. As the comet approached, its nature shifted from mystery to revelation. Early images showed no cometary features, leading some to speculate it might be an asteroid. But by July 2025, the Deep Random Survey and Lowell Discovery Telescope captured a diffuse coma with a faint tail-like elongation, proving its status as a comet. The Hubble Space Telescope, with its razor-sharp vision, soon joined the effort, resolving the coma in exquisite detail and narrowing the nucleus's diameter to less than 5.6 kilometers. Meanwhile, the James Webb Space Telescope pierced the infrared veil, revealing a coma awash in carbon dioxide and water ice, with hints of carbon monoxide and carbonyl sulfide. The comet's evolution was not static. By August 2025, the coma had deepened in redness, a sign of shifting composition as volatile ices sublimated and dust particles coalesced. The VLT detected a surge in cyanide and nickel emissions, phenomena mirrored in solar system comets but amplified here. These findings painted a picture of a dynamic world, its surface reshaping in real time as the sun's rays carved new fissures and vents. Yet 3I Atlas remained an enigma. Was its nucleus truly as small as models suggested? Or did its coma mask a larger body? And what of its age? Tracing 3I Atlas's path backward through the galaxy hinted at a startling possibility. Its trajectory originated from the Milky Way's thick disk, a region populated by ancient stars, some dating back 7 billion years. If this calculation held, the comet could be older than the solar system itself, a relic from an era when the galaxy was young and turbulent. Such a finding would rewrite our understanding of cometary origins, suggesting that interstellar objects like 3I Atlas are not rare anomalies, but remnants of a vast unseen reservoir of primordial material. Yet not all mysteries yielded to observation. The comet's parent star remains unknown, its identity buried beneath the fog of time. Theories abound. Was 3I Atlas ejected by the gravitational tug of a rogue planet? Or did it originate in a binary star system where interactions with a companion star hurled it into the void? The absence of a definitive answer only deepened the intrigue. Even as scientists debated the comet's origins, a shadowy controversy loomed. In July 2025, astrophysicist Avi Loeb speculated that 3I Atlas might be an extraterrestrial spacecraft, citing its anomalous trajectory and lack of certain chemical signatures. The claim drew sharp criticism from the scientific community, who emphasized the wealth of data pointing to a natural explanation. For every voice questioning the comet's true nature, another reaffirmed the power of observation and reason to illuminate the unknown. Through it all, 3I Atlas continued its journey, a silent witness to the interplay of forces that govern the cosmos. Its passage through the solar system was a fleeting chapter in a much longer story, one that stretched across millennia and light years. Yet for those who studied it, the comet was more than a transient visitor. It was a reminder of the universe's vastness, a challenge to our assumptions, and a promise that the next great discovery awaited just beyond the horizon. As 3I Atlas hurtles through the solar system on its unbound trajectory, it becomes a living testament to the laws of physics that govern the cosmos. Its path, defined by an orbital eccentricity of 6.14, is a cosmic arrow aimed precisely at the Sun, a trajectory so steep and direct that it defies the gentle curves of planetary orbits. Unlike the elliptical paths of comets and asteroids, which loop endlessly in the gravitational embrace of the Sun, 3I Atlas's hyperbolic course is a one-way journey. This distinction is not merely academic, it is a declaration of the comet's interstellar origin. The mathematics of orbital mechanics reveal the truth of this assertion. An object's fate is sealed by its velocity relative to the Sun. If it exceeds the escape velocity of approximately 42 kilometers per second at 1 AU, it will not return. 3I Atlas, with its hyperbolic excess velocity of 58 kilometers per second, far outpaces this threshold, ensuring its departure from the solar system. This velocity, combined with its trajectory's inclination of 5 Dirk, relative to the ecliptic, paints a picture of an object that has traveled untethered for eons, its path shaped by the gravitational tides of distant stars. But how did 3I Atlas acquire such velocity? The answer lies in the gravitational architecture of its parent star system. Simulations suggest that the comet was likely ejected during a period of intense dynamical instability, perhaps triggered by the migration of a giant planet or the disruptive influence of a passing star. These mechanisms, common in the chaotic early lives of planetary systems, can fling comets like 3I Atlas into interstellar space, where they drift for millions or even billions of years before encountering another star system. The fact that 3I Atlas's trajectory aligns with the thick disk of the Milky Way, a region dominated by ancient stars, implies that its ejection occurred in a system far older than our own, its journey a relic of an epoch when the galaxy was still forming. Yet the comet's trajectory is not merely a record of its past. It is a roadmap to the future. As 3I Atlas approaches perihelion on 29 October 2025, its velocity will peak at 68 kilometers per second, a speed that will propel it beyond the orbit of Mars and into the outer solar system. From there, it will vanish into the darkness, its path carrying it toward the galactic plane and the distant stars that lie beyond. Though it will never return to our skies, its legacy will endure in the data it leaves behind, a snapshot of a world we may never visit, but can strive to understand. With this foundation laid, the next step in our exploration of 3I Atlas must delve deeper into the heart of the comet itself. What lies beneath its coma, hidden from view by the veil of gas and dust? What secrets does its nucleus hold about the conditions of its birthplace? To answer these questions, we must turn our gaze inward, peering into the frozen depths of a world that has traversed the cosmos for eons. The journey is only beginning. In the vast tapestry of the cosmos, where stars burn like distant embers and galaxies spiral in silent dances, a solitary traveler cuts through the void. Discovered on 1 July 2025 by the asteroid terrestrial impact last alert system, Atlas. In Chile, 3I Atlas, a comet from another star system, has become a beacon of curiosity. Its arrival in our solar system is not merely a celestial event, but a profound reminder of the universe's interconnectedness. As the third interstellar object confirmed to traverse our neighborhood, 3I Atlas joins the ranks of 1I Oumuamua and 2I Borisov, each a fragment of cosmic history hurled from the cradle of another stellar family. Yet unlike its predecessors, 3I Atlas carries with it a unique story, one written in the language of ice, gas, and ancient starlight. This comet's journey began billions of years ago, long before the solar system itself coalesced from a swirling nebula. Its trajectory, a hyperbolic arc unshackled by the sun's gravity, speaks of origins far beyond our familiar realm. The sun, a mere waypoint in its endless voyage, warms its icy heart, triggering a transformation that reveals the secrets of its birthplace. As 3I Atlas glides through the inner solar system, it becomes both an enigma and a messenger, a time capsule from the cold, dark reaches of interstellar space. What can this traveler tell us about the distant star systems it once called home? And what does its passage say about the dynamic, ever-shifting nature of the universe we inhabit? To understand 3I Atlas is to peer into the abyss of cosmic history. Its nucleus, a frozen relic of primordial material, holds clues to the conditions of its birthplace. The gases it releases, the dust it sheds, and the light it reflects are all threads in a tapestry of information. Yet, as with all cosmic phenomena, the truth is veiled in complexity. The comet's nucleus is obscured by a coma of escaping ice and dust. Its true dimensions a puzzle of light and shadow. Still, humanity's instruments, telescopes on Earth and in space, strain to decipher its story, piecing together fragments of data into a coherent narrative. 3I Atlas is not just a visitor, it is a mirror held up to the cosmos. Its existence challenges our understanding of planetary systems, interstellar dynamics, and the resilience of matter in the vacuum of space. As it continues its journey outward, beyond the orbits of Mars and into the void, It leaves behind a trail of questions and a promise that the universe in its infinite expanse is far richer and stranger than we dare imagine. At the heart of 3I Atlas lies its nucleus, a solid icy core that anchors the comet's identity. Though the nucleus remains shrouded in the haze of its coma, observations by the Hubble Space Telescope suggest it is no larger than a kilometer in diameter. This minuscule size belies the comet's grandeur. For a body so small to carry the energy and momentum to escape the solar system, it must have been propelled by forces of immense scale. The nucleus, likely a jagged, irregular lump of rock and ice, is a fragile remnant of its home system, a place where gravity and chaos once reigned. The sun's influence transforms this frozen core into a spectacle of activity. As 3I Atlas approaches the sun, its nucleus is bathed in solar radiation, heating the volatile ices within. Carbon dioxide and water ice sublimate into gas, releasing pressure that fractures the nucleus's surface and expels dust into space. This process forms the Coma, a glowing envelope of gas and particulate matter that expands outward like a breath of steam from a boiling pot. The Coma's reddish hue, observed by multiple telescopes, hints at the presence of complex organic molecules irradiated by the relentless march of time and cosmic rays. The nucleus's rotation, estimated at approximately 16.7 hours, further complicates its behavior. Like a spinning top, it wobbles under the weight of its own asymmetry, causing fluctuations in brightness as different facets of its surface reflect sunlight. These variations, though subtle, offer glimpses into the nucleus's structure, yet the Coma's obscuring veil makes precise measurements elusive. Astronomers must sift through layers of data, light curves, spectroscopic signatures, and imaging to reconstruct the nucleus's shape and composition. What makes 3I Atlas particular is its prodigious outflow of material. At a rate of 60 kilograms of dust per second, the comet sheds its outer layers as if resisting its own demise. This erosion is not merely a consequence of solar heating, but a testament to the nucleus's fragility. Smaller than most comets in the solar system, 3I Atlas's nucleus is a paradox, delicate enough to disintegrate yet resilient enough to endure the tumultuous journey from interstellar space. How did such a fragile object survive the gravitational slingshots of its home system? And what forces shaped its structure before it became a solitary traveler? The answer may lie in the comet's origin. Tracing its trajectory backward, astronomers find its path diverges from the plane of the solar system, tilting 175 degrees in a retrograde orbit. This trajectory suggests a violent ejection, perhaps from a system where gravitational interactions among planets or passing stars hurled it into the void. Such an origin implies a history of chaos, a dance of celestial bodies, where order and destruction coexist. The nucleus's survival is a victory of randomness over entropy, a reminder that even the smallest fragments of the cosmos can endure the unforgiving void. Yet for all its resilience, 3I Atlas is ephemeral. Its journey through the inner solar system is fleeting, a brief interlude in a life spanning billions of years. As it nears perihelion, the point of closest approach to the sun, its activity will peak, and its coma will swell to dimensions rivaling planetary scales. But this moment of brilliance is also its reckoning. The sun's heat will accelerate the comet's disintegration, reducing its nucleus to a husk and scattering its dust into the solar wind. By the time 3I Atlas exits the solar system, it may be little more than a ghost of its former self, its story etched in the trails of gas and ice it leaves behind. The survival of 3I Atlas's nucleus defies expectations. To endure ejection from its home system, it must have formed in a region of intense gravitational turbulence. Such environments are often found in young star systems, where massive planets or binary stars stir the protoplanetary disk into a maelstrom of colliding debris. In these chaotic crucibles, small icy bodies like comets are born, but they are also easily lost, flung into the void by the gravitational tides of giants. That 3I Atlas escaped its system intact is a testament to its fortuitous origin. Perhaps it formed in a stable, distant orbit, shielded from the gravitational chaos of its planetary neighbors. Or maybe it was born in a system where such chaos was absent, a quiet world where icy bodies accumulated undisturbed. Either way, the comet's journey through interstellar space is a story of endurance. For billions of years, it has traversed the vacuum, subjected to the relentless radiation of the Milky Way and the occasional gravitational tug of passing stars. The fact that it remains intact, despite these trials, raises questions about the durability of interstellar objects. Are comets like 3I Atlas rare survivors, or do countless others disintegrate before reaching the solar system? If the latter, then our detection of such objects is a stroke of luck, a glimpse into a hidden population of interstellar wanderers. The nucleus's small size amplifies these questions. In the solar system, comets with diameters under a kilometer are uncommon, often fragmented remnants of larger bodies. Yet 3I Atlas's diminutive stature suggests it may never have grown beyond its current size. This raises the possibility that it formed in a region of its home system, where material was scarce, or where its growth was stunted by competing gravitational forces. Such a scenario challenges conventional models of comet formation, which assume that comets grow from the gradual accumulation of ice and dust in the outer reaches of planetary systems. If 3I Atlas is representative of a broader class of interstellar comets, then our understanding of how these objects form and how they populate the galaxy must be revised. Moreover, the comet's survival has implications for the study of interstellar chemistry. The nucleus of 3I Atlas is a repository of primordial material, untouched by the geological and atmospheric processes that shape planets. Its composition, preserved for eons, offers a window into the conditions of its birthplace. The presence of carbon dioxide, water ice, and organic compounds in its coma suggests that its parent star system was rich in volatile materials, possibly forming in a region of the galactic disk where such substances were abundant. Yet the scarcity of heavier elements, such as iron, hints at a different evolutionary path. Was its parent star metal poor, or did the comet's formation occur in a zone where such elements were rare? These questions bridge the gap between stellar astrophysics and planetary science, revealing the intricate connections between stars and the worlds they create. The study of 3I Atlas also underscores the challenges of observing interstellar objects. From our vantage point, these visitors are faint and fleeting, their paths difficult to predict. Even with advanced telescopes, the nucleus of 3I Atlas remains a shadowy silhouette, its true nature obscured by the coma it sheds. This obscurity is a reminder of the limits of human perception in the vastness of space. Yet it is precisely this limitation that drives innovation. The quest to unravel the mysteries of 3I Atlas has spurred advancements in observational techniques, from adaptive optics to spectroscopy, each tool pushing the boundaries of what is possible. Perhaps the greatest lesson of 3I Atlas is its role as a cosmic bridge. It is a link between star systems, a fragment of another world's history now embedded in ours. Its passage through the solar system is not an isolated event, but a chapter in a much larger story, one that spans galaxies, epochs, and the fundamental forces that govern existence. In studying 3I Atlas, we are not merely observing a comet. We are listening to the echoes of a universe in motion, a symphony of creation and destruction played out across the void. As 3I Atlas's nucleus erodes, it unleashes a cascade of chemical revelations. The gases and dust it emits are more than mere byproducts of its journey. They are messages from its past, encoded in molecular structures and isotopic ratios. These emissions, analyzed by telescopes like the James Webb Space Telescope and the Very Large Telescope, paint a portrait of a comet that is both alien and familiar. Carbon dioxide, water vapor, and cyanide gas swirl in its coma, their proportions offering clues to the conditions of its birthplace. Yet the comet's chemistry is not static. It evolves as the nucleus interacts with the sun, each phase of sublimation altering its composition. This dynamic interplay between ice and heat is a microcosm of the universal processes that shape worlds, from the icy moons of Jupiter to the distant Kuiper belt. The next segment delves into the heart of this transformation, the coma and tail that surround and trail 3I Atlas. Here, the interplay of solar radiation, magnetic fields, and the comet's own volatile materials creates a spectacle of cosmic artistry. The Coma's reddish hue, the elongation of its dust plumes, and the faint shimmer of its ion tail are not random phenomena, but the fingerprints of chemistry in action. To understand these features is to grasp the essence of a comet's life cycle, a cycle that mirrors the birth and death of stars themselves. On 1 July 2025, deep in the skies above Chile's Rio Hurtado, a new chapter in humanity's exploration of the cosmos began with the discovery of 3I Atlas. This interstellar comet, hurtling through the inner solar system at an astonishing speed of 58 kilometers per second, marked itself as the third confirmed visitor from the depths of interstellar space. Its arrival was not a silent event. It carried the echoes of distant stars and the secrets of a long-forgotten celestial past. As the asteroid terrestrial impact last alert system, Atlas, captured the first glimpses of this wandering traveler, it became clear that 3I Atlas was unlike any other object observed within our cosmic neighborhood. The moment of discovery was both humbling and electrifying. For millennia, comets have captivated human imagination, appearing as fleeting spectacles in the night sky. Yet 3I Atlas was different. It did not originate from the familiar realms of the Kuiper Belt or the distant Oort cloud. Instead, it came from beyond the boundaries of our solar system, a relic of another star system's turbulent history. Its trajectory, a hyperbolic path bending sharply around the sun before continuing its journey into the void, confirmed its interstellar nature. This was not a transient guest bound to the gravitational dance of our planetary family. It was a true nomad of the cosmos, traversing the vast expanse between the stars. As 3I Atlas approached, the scientific community turned its gaze toward the comet, eager to decode its mysteries. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories around the world joined forces to study its luminous coma and the faint tail stretching into the darkness. With every observation, a clearer picture emerged of this ancient wanderer, one that had traveled billions of kilometers across the interstellar void, guided by the invisible currents of the Milky Way. What lay beneath its glowing veil of gas and dust remained a tantalizing enigma, waiting to be unraveled by the relentless pursuit of knowledge. As 3I Atlas continued its journey through the inner solar system, astronomers worked tirelessly to decipher its origins and nature. The initial observations revealed a comet in full activity, its nucleus cloaked in a coma of gas and dust, illuminated by the sun's warming embrace. The Hubble Space Telescope played a pivotal role in characterizing the comet, capturing high-resolution images that hinted at the size and behavior of its core. These images, combined with data from the James Webb Space Telescope, painted a complex portrait of a celestial object unlike any seen before. Unlike the comets of our own solar system, which often exhibit predictable patterns of activity, 3I Atlas displayed an unusual richness in carbon dioxide, a finding that sparked immediate intrigue among researchers. The discovery of carbon dioxide in such abundance raised fundamental questions about the comet's composition and history. Typically, comets within the solar system contain a mixture of water ice, carbon monoxide, and other volatiles, but the dominance of carbon dioxide in 3I Atlas suggested a different formation environment. Was this comet born in a distant stellar nursery, where carbon dioxide was more prevalent, or had it undergone a transformation during its long interstellar voyage, shaped by the harsh conditions of deep space? The answers to these questions lay buried beneath layers of dust and ice, waiting for the keen eyes of telescopes and spectrometers to penetrate the veil beyond its chemical makeup. 3I Atlas's trajectory offered another layer of insight. Its hyperbolic path, with an orbital eccentricity of 6.141, the highest recorded among interstellar objects, indicated that it had never been gravitationally bound to the sun. This meant that 3I Atlas had not merely drifted into the solar system by chance, but had followed a precise path, dictated by the unseen forces of the galaxy. Astronomers traced its motion backward through time, seeking to uncover the region of the Milky Way from which it had originated. The results pointed to the galactic center, a vast expanse teeming with stars, nebulae, and the remnants of ancient cosmic collisions. This revelation hinted at a dramatic birthplace, where violent stellar interactions may have propelled the comet from its native system into the interstellar abyss. Yet, despite the wealth of data accumulating, uncertainties remained. The size of 3I Atlas's nucleus, for instance, was still shrouded in ambiguity. The comet's Coma, a luminous cloud of gas and dust surrounding its core, complicated efforts to determine its true dimensions. Early estimates suggested a nucleus ranging from 0.32 to 5.6 kilometers in diameter, but the presence of reflective dust particles made it difficult to distinguish the nucleus from the surrounding haze. This challenge underscored the complexity of studying interstellar comets, objects that by their very nature exist at the fringes of our observational capabilities. With each new observation, the enigma of 3I Atlas deepened, revealing clues about its past and hinting at the forces that had shaped its journey. The comet's trajectory, as meticulously reconstructed by astronomers, told a story of a celestial wanderer originating from the distant reaches of the galaxy. By analyzing its hyperbolic excess velocity and orbital parameters, scientists sought to pinpoint its place of origin within the Milky Way. The results were nothing short of astounding. 3I Atlas had likely originated from the galactic disk, a region populated by stars with varying ages and compositions. More intriguingly, some analyses suggested that the comet might have hailed from the thick disk, a component of the Milky Way that hosts some of the oldest known stars. If true, this would imply that 3I Atlas had formed billions of years ago, predating the solar system itself. The implications of such an ancient origin were profound. If 3I Atlas had indeed formed in the early days of the Milky Way, it would carry with it the chemical signature of a vastly different cosmic epoch. Unlike the comets of our own solar system, which reflect the conditions of the protoplanetary disk that gave rise to the planets, 3I Atlas might preserve the remnants of a primordial interstellar environment. Its composition, particularly the dominance of carbon dioxide, could serve as a window into the chemistry of distant star systems, offering insights into the building blocks of worlds beyond our own. Could this comet have formed around a red dwarf star, where carbon dioxide was more abundant, or had it emerged in a dense molecular cloud, where the cold vacuum of space allowed volatile compounds to freeze into solid form? The search for 3I Atlas's parent star added another layer of complexity to its story. Unlike objects within the solar system, which can be traced back to their point of origin based on orbital dynamics, interstellar comets posed a greater challenge. Over the billions of years it had spent adrift in the galaxy, 3I Atlas had likely encountered countless stars, its trajectory subtly altered by gravitational tugs and cosmic encounters. Tracing its path back in time, however, revealed that it had passed within a mere parsec of 25 known stars in the recent past. Among these, some were candidates for its origin, stars with compositions and ages that matched the comet's inferred properties. Yet without definitive evidence, the question of its birthplace remained open, a mystery waiting to be unraveled by future discoveries. Even as scientists grappled with the comet's origins, another puzzle emerged from its chemical composition. The James Webb Space Telescope's observations revealed not only an abundance of carbon dioxide, but also traces of water ice, carbon monoxide, and carbonyl sulfide. The presence of these compounds suggested that 3I Atlas had once been embedded in a cold, distant region of its parent system, where volatile materials could condense into solid form. The fact that water ice was present, albeit in smaller quantities, hinted at a dynamic evolutionary history, one in which the comet had experienced periods of heating and sublimation, altering its surface and interior over time. What then had driven 3I Atlas from its home system? The most plausible explanation was a gravitational slingshot effect, a process in which a massive celestial body, such as a giant planet or a passing star, could hurl an object into interstellar space. Such events were not uncommon in the early stages of planetary systems, where gravitational interactions between forming planets and their debris could eject material into the void. If 3I Atlas had been expelled in this manner, it would have embarked on a journey lasting millions, if not billions of years before finally reaching the solar system. This realization underscored the comet's role as a cosmic messenger, an object carrying the memory of a distant star system's tumultuous past. Among the most striking revelations about 3I Atlas was its extraordinary composition, particularly the dominance of carbon dioxide in its coma. The James Webb Space Telescope's spectroscopic observations revealed a CO₂ to water mixing ratio of 8:1 anomaly that defied conventional wisdom about cometary chemistry. In contrast, typical comets from the solar system exhibit a much lower CO₂ to water ratio, usually less than 1:1, with water ice playing a dominant role in their outgassing. The sheer abundance of carbon dioxide in 3I Atlas suggested a radically different formation environment, one where CO₂ was more readily available and possibly more stable than water ice. This raised a compelling question: had the comet formed in a region where carbon dioxide was the primary volatile, or had some external factor suppressed the sublimation of water? One possible explanation for this CO₂-rich composition was that 3I Atlas had originated in a protoplanetary disk where carbon dioxide was more prevalent than water. In such an environment, CO₂ could have condensed into solid form at greater distances from the parent star than water ice, allowing it to dominate the comet's composition. This scenario implied that the comet's parent system was chemically distinct from the solar system, perhaps forming around a star with a different elemental abundance. Alternatively, the high CO₂ content could have resulted from a unique evolutionary history, where the comet's surface had developed an insulating crust that shielded subsurface water from sublimation. If this were the case, the comet might be releasing CO₂ more efficiently than water, giving the illusion of a higher CO₂ abundance. The presence of carbon monoxide and carbonyl sulfide in 3I Atlas's Coma added further complexity to its chemical profile. These compounds, while not unheard of in solar system comets, were present in proportions that deviated from the norm. Carbon monoxide, for instance, is typically found in comets that originate from the outermost reaches of the solar system, where temperatures are low enough for it to remain frozen. The fact that 3I Atlas exhibited a CO₂-to-water ratio similar to solar system comets suggested that it had retained some similarities to its local counterparts, despite its interstellar origins. Meanwhile, the detection of carbonyl sulfide, a compound rarely observed in cometary studies, hinted at a chemical pathway unique to 3I Atlas or its parent system. The implications of this CO₂-enriched composition extended beyond the comet itself. If 3I Atlas had indeed formed in a different stellar system, its chemistry could provide valuable insights into the diversity of planetary formation processes across the galaxy. Comets are often regarded as pristine relics of their birth environments, preserving the chemical fingerprints of the protoplanetary disks in which they were born. By studying 3I Atlas, scientists could gain a rare glimpse into the conditions that shaped another star system's icy bodies, potentially revealing whether such systems share commonalities with the solar system or represent entirely different evolutionary paths. Moreover, the presence of heavy isotopes of carbon in CO₂ molecules raised intriguing possibilities about the comet's exposure to interstellar radiation. Isotopic ratios can serve as a cosmic clock, offering clues about the duration and intensity of a comet's journey through space. If 3I Atlas had spent billions of years adrift in the galaxy, its CO₂ molecules might have been subjected to cosmic ray bombardment, altering their isotopic composition in ways that could be detected through spectroscopy. Understanding these changes could help astronomers determine how long the comet had been traveling and whether its chemical makeup had been modified by the harsh conditions of interstellar space. As the scientific community delved deeper into the comet's composition, the mystery of its CO₂ abundance continued to unfold. Was this a unique quirk of 3I Atlas, or did it represent a broader class of interstellar comets with similarly unconventional chemistries? The answers to these questions would not only refine our understanding of cometary formation, but also shed light on the vast uncharted tapestry of the cosmos. Beyond its peculiar composition, 3I Atlas's existence carries profound implications for our understanding of the universe. As the third confirmed interstellar object to traverse the solar system, it stands as a testament to the dynamic and interconnected nature of the cosmos. Unlike 1I Oumuamua and 2I Borisov, which were primarily studied for their trajectories and physical characteristics, 3I Atlas offers a unique opportunity to explore the chemistry of an interstellar comet in unprecedented detail. Its passage through the inner solar system allows scientists to analyze its outgassing in real time, providing a rare chance to compare its composition with that of comets within our own system. This comparison could reveal whether the processes that shape comets are universal or vary significantly depending on the stellar environment in which they form. Furthermore, the discovery of 3I Atlas reinforces the idea that the Milky Way is a vast reservoir of interstellar material, with objects constantly drifting between star systems. While most comets within the solar system originate from the Oort cloud, a spherical shell of icy bodies extending up to 100,000 astronomical units from the Sun, interstellar comets like 3I Atlas remind us that the boundaries of our cosmic neighborhood are porous. These interstellar visitors are not anomalies, but rather a natural consequence of the galaxy's gravitational architecture, where the movements of stars and planetary systems create a continuous exchange of material. By studying 3I Atlas, scientists can better understand how frequently such interstellar encounters occur and what role they play in shaping the evolution of planetary systems. The potential for future interstellar comets to be discovered is equally exciting. As observational technology continues to advance, the likelihood of detecting more of these celestial wanderers increases. Future missions, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, will significantly enhance our ability to identify and track interstellar objects, opening a new era of interstellar astronomy. With each new discovery, our understanding of the galactic ecosystem will deepen, revealing the intricate web of interactions that govern the movement of matter across the vast expanse of space. In the broader context of cosmic history, 3I Atlas serves as a reminder of the universe's boundless scale and the impermanence of celestial phenomena. While the comet will soon leave the solar system, its journey is far from over. It will continue its voyage through the interstellar void, perhaps encountering other stars and planetary systems in the distant future. In this way, 3I Atlas is not just a visitor to our cosmic backyard, but a participant in the grand, ongoing story of the galaxy. Its presence challenges us to think beyond the confines of our own system and to recognize that the universe is a place of constant exchange, where the remnants of distant worlds drift endlessly through the dark, carrying with them the secrets of their origins. As scientists continue to analyze the data gathered from 3I Atlas, its legacy will endure as a beacon of discovery. It represents not only the culmination of decades of astronomical research, but also the beginning of a new chapter in our quest to understand the cosmos. With every observation, we edge closer to answering fundamental questions about the nature of interstellar objects, the diversity of planetary systems, and the forces that govern the distribution of matter across the galaxy. And as we stand beneath the night sky, watching 3I Atlas vanish into the depths of space, we are reminded that the universe is a place of infinite wonder, where even the smallest fragments of distant worlds hold the key to unlocking the greatest mysteries of all. In the vast, silent expanse of interstellar space, comets are transient messengers, their fleeting appearances in our solar system offering glimpses into the distant, frigid reaches of the galaxy. Among them, 3I Atlas stands apart, not merely as a visitor from another star system, but as a bearer of ancient secrets encoded in its tenuous coma. Amper's comet's coma, often described as its breath, is a fragile halo of gas and dust that forms as the nucleus is warmed by the sun's distant touch. For 3I Atlas, this breath is anything but ordinary. It is a spectral fingerprint, a kaleidoscope of volatile compounds and organic molecules that defy easy categorization. The coma of this interstellar wanderer is not just a transient phenomenon. It is a record of the conditions under which it was born, a testament to the chemistry of a faraway star system, and a clue to the comet's age, origins, and journey through the cosmos. As we peer into the coma of 3I Atlas, we are not merely observing a cloud of gas and dust. We are deciphering a message written in the language of chemistry and physics. What does this message say? How does it differ from the comas of comets born in our own solar system? And what does it tell us about the nature of interstellar objects, which are still shrouded in mystery. The answers lie in the intricate dance of particles and radiation that shapes the coma, a process both delicate and dynamic. The coma of 3I Atlas is a sprawling, invisible tapestry of material, stretching outward from the nucleus in a radius of 348,000 kilometers, a distance greater than the diameter of Earth itself. This immense structure is dominated by carbon dioxide gas, a rarity in the comas of solar system comets, which typically emit water vapor in greater quantities. The James Webb Space Telescope, JWST, has revealed that the coma is a veritable treasure trove of volatile compounds: water ice, water vapor, carbon monoxide, and carbonyl sulfide, alongside the abundant CO₂. These substances do not exist in isolation. They interact in complex ways, forming transient chemical bonds and reacting to the solar wind and radiation. What gives the coma its distinctive reddish hue? The answer lies in the dust particles that accompany the gaseous outflows. These particles, ranging from submicron to several micrometers in size, are composed of irradiated organic compounds, carbon-rich molecules, that have been altered by eons of exposure to cosmic radiation. The red coloration mirrors that of D-type asteroids, suggesting a shared heritage in the chemistry of the outer solar system. Yet the dust in 3I Atlas's coma is not uniform. Smaller grains ejected at velocities of up to 22 meters per second spiral outward under the pressure of sunlight, while larger grains, moving at a mere 2 meters per second, cling closer to the nucleus, forming a denser, more structured layer. This stratification creates a layered, almost stratified atmosphere around the comet, a delicate balance of forces that governs the distribution of material. The dynamics of the coma are further complicated by the comet's unique trajectory. As 3I Atlas hurtles through the inner solar system at a blistering 58 kilometers per second, its hyperbolic path ensures that it will not linger long enough for the sun's influence to fully dominate its activity. Yet even at a distance of 1.36 astronomical units, AU, from the sun, the comet is already undergoing significant changes. The Hubble Space Telescope has captured images revealing a coma that is both expansive and evolving, with a sun-facing plume of dust and gas extending in the direction of the sun, a stark contrast to the anti-solar tails typically observed in comets. This plume, a result of enhanced sublimation on the sunlit side of the nucleus, underscores the asymmetry of the comet's activity, a feature that may provide clues to the orientation and rotation of its nucleus. The composition of 3I Atlas's coma is not merely a curiosity. It is a Rosetta Stone for understanding the comet's origins. The dominance of CO₂ over water vapor is particularly striking. In solar system comets, water ice is the primary volatile component, sublimating readily as the comet approaches the sun. However, 3I Atlas's coma tells a different story. The high CO₂ abundance suggests that the comet formed far from its parent star. Beyond the CO₂ frost line, the boundary in a protoplanetary disk where temperatures are low enough for CO₂ to condense into solid form. This places 3I Atlas in a category akin to the Oort cloud comets of our own solar system, which originate from the distant cold peripheries of planetary systems. Yet the absence of water ice in significant quantities raises intriguing questions. Did the parent star system of 3I Atlas lack sufficient water to form comets like those in the solar system? Or does the comet's nucleus harbor a thick, insulating crust that shields buried water ice from the sun's warming rays? The absence of carbon chain compounds in 3I Atlas's coma adds another layer of complexity. Carbon chains such as C2 and C3 are common in the comas of solar system comets, where they contribute to the production of complex organic molecules. Their scarcity in 3I Atlas suggests a chemical environment that is either inherently deficient in these precursors, or one in which they are rapidly destroyed by radiation or other processes. This depletion could hint at the comet's age, if 3I Atlas is indeed 7 to 14 billion years old. As some studies suggest, the gradual breakdown of organic molecules over eons might explain the observed deficiency. Alternatively, the parent star system could have lacked the necessary conditions for the synthesis of carbon chains in the first place. Either scenario challenges our understanding of the diversity of cometary chemistry in the galaxy. The detection of cyanide gas, CN, and atomic nickel vapor in the Coma further deepens the mystery. While CN is a familiar sight in cometary spectra, the presence of nickel, an element typically associated with metallic cores rather than icy bodies, is unexpected. Theories abound. Perhaps nickel is liberated from organic compounds containing nickel atoms, such as nickel tetracarbonyl, through chemical decomposition driven by solar radiation. Or maybe the comet's nucleus contains trace amounts of metallic minerals, which are vaporized as the nucleus warms. Either possibility opens a window into the internal structure of 3I Atlas, though the lack of direct sampling leaves many questions unanswered. Perhaps the most profound implication of the Coma's composition is its potential to reshape our understanding of interstellar comets as a class. 3I Atlas is the third such object discovered, but its uniqueness, its CO₂-rich coma, its alignment with the ecliptic plane, its age suggests that interstellar comets may not be homogeneous in their origins or properties. If future discoveries reveal a wide range of compositions and trajectories, it could indicate that these objects originate from diverse stellar environments, each shaped by the unique history of its home system. In this context, 3I Atlas is not just an outlier. It is a harbinger of a broader, more complex picture of the galaxy's icy population. As 3I Atlas continues its journey through the inner solar system, its coma is not the only spectacle it offers. With each passing day, the sun's influence grows stronger, and the comet's tail begins to take shape. Unlike the coma, which is a diffuse spherical envelope, the tail is a linear extension of material, sculpted by the solar wind and radiation pressure. The first signs of this transformation are subtle. A faint, broad plume of dust and gas that stretches away from the sun, marking the beginning of the comet's farewell to the solar system. The tail will soon become a defining feature of 3I Atlas, a luminous record of its interaction with the sun. As the comet approaches perihelion on 29 October 2025, the tail will grow in length and complexity, its structure revealing the dynamics of the coma and the forces at play. Observers from Earth may glimpse this tail in the twilight sky, a fleeting reminder of the comet's passage. Meanwhile, spacecraft orbiting Mars and Jupiter will capture more detailed views, providing insights into the tail's composition and behavior. Yet the tail is more than a visual marvel. It is a continuation of the coma's story. Just as the coma encodes the chemistry of the comet's origins, the tail will encode the physics of its final moments in the solar system. The interplay between the tail's dust and gas, the solar wind, and the comet's own motion will create patterns that may help scientists unravel the mysteries of 3I Atlas's nucleus and its ultimate fate. As we shift our focus from the coma to the tail, we move from the intimate details of the comet's birthplace to the grand, sweeping arcs of its departure, a transition that promises new revelations in the saga of this interstellar traveler. In the vast, silent expanse of the cosmos, where time stretches into epochs and distances defy comprehension, 3I Atlas arrives, a lonely traveler from another corner of the galaxy. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile, this interstellar comet is a relic of ancient processes, a fragment of a distant star system hurtling through our solar system on a trajectory that defies the sun's gravitational embrace. Its name, 3I Atlas, marks it as the third interstellar object ever confirmed to pass through our celestial neighborhood, following the enigmatic 1I Oumuamua 2017 and the mysterious 2I Borisov 2019. Yet 3I Atlas is no mere visitor. It is a storyteller carrying clues about the birth of stars, the evolution of planetary systems, and the chaotic dance of matter across the Milky Way. When 3I Atlas was first glimpsed, it was already a prodigious distance from the Sun, over 4.5 astronomical units, AU away, a realm colder than Pluto's orbit. But its speed betrayed its true nature: 58 kilometers per second, 36 miles per second. a velocity far exceeding the escape speed of the solar system. This hyperbolic excess velocity, imparted by the gravitational forces of its home system, ensures that 3I Atlas will not linger. It will pass through our system in a fleeting, elegant arc, brushing the orbits of Mars and Venus before vanishing into the void. Its journey is brief in cosmic terms, yet its impact on human understanding is profound. What makes 3I Atlas remarkable is not merely its origin, but its transformation as it interacts with the Sun. Like all comets, it is a time capsule of primordial material, a ball of ice and rock forged in the frigid outskirts of a distant star. Yet unlike the comets that originate from the Kuiper belt or Oort cloud, 3I Atlas carries the imprint of a foreign stellar nursery. Its nucleus, shrouded in a coma of gas and dust, glows faintly as it sublimates under solar radiation. Observations by the Hubble and James Webb Space Telescopes reveal a composition unlike anything seen in our solar system. An abundance of carbon dioxide, traces of water ice, and the telltale signature of cyanide and nickel. These ingredients paint a picture of a world born in the cold, dark reaches of a protoplanetary disk, ejected long ago by gravitational chaos, and now wandering the galaxy alone. As 3I Atlas approaches its closest point to the Sun, perihelion on 29 October 2025, its story unfolds. The comet will not come near Earth, but it will pass within 0.19 AU of Mars, offering orbiters a rare opportunity to study it up close. For now, telescopes on Earth and in space track its progress, unraveling the secrets of its structure, age, and origin. What emerges is a tale of cosmic scale, a comet that may be older than our solar system itself, a wanderer from the Milky Way's thick disk, a relic of a time when stars and planets were forming in the galaxy's ancient heart. 3I Atlas is not just a passing curiosity, it is a bridge between the familiar and the alien, a reminder that the universe is teeming with stories waiting to be told. To understand 3I Atlas is to dissect the anatomy of a celestial nomad. At its core lies a nucleus, a solid icy body that serves as the source of the comet's activity. Though its exact size remains elusive, estimates from Hubble observations place its diameter between 0.32 and 5.6 kilometers, 0.2 to 3.5 miles, with the most probable measurement being less than 1 kilometer, 0.62 miles. This diminutive nucleus is dwarfed by the coma that envelops it, a glowing cloud of gas and dust extending thousands of kilometers into space. The coma forms as solar radiation heats the nucleus, sublimating its frozen reservoirs of carbon dioxide, water, and other volatile ices. These gases erupt in jets, carrying dust particles into the vacuum, where they scatter sunlight and create the comet's ethereal glow. The composition of 3I Atlas's coma is a window into its alien heritage. Unlike comets in our solar system, which typically contain a mix of water ice, ammonia, and methane, 3I Atlas is unusually rich in carbon dioxide. Observations by the James Webb Space Telescope, JWST, reveal that CO2 constitutes the majority of the gases escaping from its nucleus, with water ice and vapor present in smaller quantities. This imbalance suggests a formation history distinct from our own. Perhaps 3I Atlas originated in a protoplanetary disk, where CO2 dominated over water, or its surface has been altered by prolonged exposure to cosmic radiation. The presence of carbon monoxide and carbonyl sulfide adds complexity to its chemistry, hinting at a turbulent past shaped by stellar winds and interstellar collisions. Equally intriguing is the detection of cyanide gas and atomic nickel vapor in its coma. These elements, though rare in comets, are not unheard of. The Very Large Telescope, VLT, recorded their presence in August 2025, noting a rapid increase in concentration as the comet neared the Sun. The emission of nickel is particularly curious, as it is typically associated with the breakdown of nickel-containing organic compounds, a process that could be accelerated by the intense radiation from nearby stars. The absence of iron, however, raises questions about the comet's internal structure and the mechanisms driving its outgassing. Is 3I Atlas a remnant of a metal-poor star system? Or does its composition reflect the unique conditions of its birthplace, a region of the galaxy where heavy elements were scarce. The dynamics of 3I Atlas's Coma and tail further illuminate its behavior. By August 2025, its tail had stretched to 56,000 kilometers, 35,000 miles, a ribbon of fine dust particles propelled by solar radiation pressure. Yet the tail's orientation pointing eastward, away from the sun, is only part of the story. Simultaneously, a sun-facing plume of dust extends toward the comet's illuminated hemisphere, a feature observed in distant comets like C2014 UN271, Bernardinelli, Bernstein. This dual morphology suggests that 3I Atlas's nucleus is unevenly heated, with active regions concentrated on one side. The plume's persistence over weeks indicates a stable source of outgassing, perhaps a fissure or hotspot on the nucleus's surface. The interplay between 3I Atlas's nucleus and Coma is a delicate balance of physics and chemistry. As the comet approaches perihelion, the sun's energy will intensify its activity, causing the Coma to expand and the tail to lengthen. Yet the rate of this transformation depends on the nucleus's structure. If it is porous, the sublimation of ices could trigger sudden outbursts, releasing bursts of dust and gas. If it is compact, the activity may remain steady, producing a gradual, graceful evolution. Either scenario offers insights into the resilience of interstellar comets and the extremes they endure as they traverse the galaxy. At the heart of this process is the nucleus's rotation. Though obscured by the Coma, 3I Atlas's nucleus is likely irregularly shaped, like a lumpy potato. This irregularity causes periodic variations in brightness as it spins, a phenomenon observed in other comets. Early studies suggest a rotation period of approximately 16 to 17 hours, but the exact value remains uncertain. The orientation of the rotation axis is equally enigmatic. Observations by the Hubble Space Telescope hint that the nucleus's north pole may point towards specific coordinates in the sky, aligning its activity with the sun's pull. Understanding this alignment is key to predicting how 3I Atlas will behave as it continues its journey. The composition of 3I Atlas's Coma also holds clues to its age. The presence of amorphous water ice, as opposed to the crystalline ice common in solar system comets, suggests that it has spent millennia in deep freeze, shielded from the sun's rays. Similarly, the high abundance of CO2 may indicate a formation environment where temperatures were low enough for this gas to condense into solid form. These details, combined with the comet's trajectory, point to an origin in the Milky Way's thick disk, a stellar population billions of years older than our solar system. If confirmed, 3I Atlas would be a relic from a time when the galaxy was young, its material shaped by the first generations of stars. Yet for all its alien qualities, 3I Atlas shares fundamental similarities with comets from our own backyard. Its dust particles, though larger than those of typical solar system comets, follow the same principles of solar radiation pressure, drifting outward to form a tail. Its outgassing mechanisms mirror those of 2I Borisov, the previous interstellar comet, suggesting that interstellar comets may share a common evolutionary pathway. And like all comets, 3I Atlas is a transient spectacle, a fleeting glimpse of the building blocks of worlds scattered across the cosmos by the gravitational tides of stars. The study of 3I Atlas transcends its individual journey. It offers a lens through which we can peer into the broader tapestry of the Milky Way. By analyzing its trajectory, composition, and age, astronomers seek to answer questions that span the history of our galaxy. Where did 3I Atlas originate? What conditions shaped its formation? How do interstellar comets contribute to the exchange of materials between star systems? These inquiries are not merely academic. They challenge our understanding of planetary formation and the interconnectedness of the cosmos. One of the most striking revelations about 3I Atlas is its potential age. If it indeed hails from the Milky Way's thick disk, a population of stars thought to be 7 to 14 billion years old, the comet could predate the solar system by billions of years. This would make 3I Atlas a relic from the galaxy's formative era, a time when massive stars burned brightly, supernovae sculpted the interstellar medium, and protoplanetary disks coalesced into planetary systems. Such an ancient origin raises profound questions. Could 3I Atlas have formed in a different stellar nursery, one that has since dissolved or merged with others? Did it witness the birth of the first stars, or the violent collisions that forged the Milky Way's spiral arms? The comet's trajectory provides further clues to its provenance. Tracing its path backward through the galaxy reveals that 3I Atlas approached the solar system from the direction of the constellation Sagittarius, near the galactic center. This origin is unusual, as most interstellar objects are predicted to arrive from the solar apex, the direction of the sun's motion through the galaxy. The fact that 3I Atlas came from the opposite hemisphere suggests that interstellar comets may not be evenly distributed across the Milky Way. Perhaps the thick disk with its older, more dispersed stars harbors a greater number of such wanderers. Alternatively, the comet's trajectory could be the result of gravitational interactions with massive stars or molecular clouds, which perturb the orbits of interstellar bodies and send them careening into the galactic plane. The high vertical velocity component of 3I Atlas, its motion perpendicular to the galactic plane, adds another layer of complexity. At 18.5 kilometers per second, 11.5 miles per second, this velocity is significantly higher than that of nearby stars, indicating that 3I Atlas follows a tilted orbit around the Milky Way. Such an orbit is characteristic of thick disk members, whose trajectories are more chaotic than those of the younger, disk-bound stars in the thin disk. This classification implies that 3I Atlas's parent star system formed in a denser, more turbulent region of the galaxy, where gravitational encounters between stars were frequent. In such an environment, comets and asteroids could be easily ejected, becoming interstellar vagabonds. The chemical fingerprint of 3I Atlas also hints at its origins. Its CO₂-rich composition contrasts with the water-dominated comas of solar system comets, suggesting a different formation environment. In protoplanetary disks, CO₂ freezes into solid form at temperatures colder than those required for water ice, meaning 3I Atlas likely formed farther from its parent star than typical comets. This distance would place it beyond the CO₂ frost line, a boundary analogous to the snow line in our solar system, where volatile ices can condense into solid form. The presence of amorphous water ice further supports this idea, as such ice is preserved in the absence of prolonged solar heating. Together, these clues paint a picture of a comet born in the outer reaches of a distant star system, ejected by gravitational interactions with giant planets or passing stars, and now adrift in the galaxy. Yet the story of 3I Atlas is incomplete without considering its potential encounters with other stars. Over its billions of years of travel, the comet has likely passed within a light year of multiple stars, each interaction subtly altering its trajectory and composition. AMPER's 2025 study by Oumuamua and collaborators identified 25 such encounters within the past 10 million years, suggesting that 3I Atlas has been influenced by the gravitational tides of the Milky Way. These encounters may have stripped away layers of its surface, exposing deeper, pristine material, or infused it with contaminants from other systems. The comet's current state is thus a palimpsest of countless journeys, a record of the dynamic interplay between stars and the debris they cast off. The implications of these findings extend beyond 3I Atlas itself. If interstellar comets are common, they could serve as cosmic couriers, transporting organic molecules and water between star systems. This process, known as panspermia, posits that life's building blocks, or even microbial organisms, could hitch rides on interstellar bodies, seeding the galaxy with the ingredients for biology. While 3I Atlas does not appear to carry signs of life, its carbon-based chemistry and the presence of complex molecules like cyanide and carbonyl sulfide support the idea that such materials are widespread in the galaxy. Future studies of interstellar comets may therefore provide critical insights into the origins of life and the universality of its precursors. Moreover, the observation of 3I Atlas underscores the importance of continued astronomical surveys. The fact that it was discovered relatively late, despite being tracked by multiple telescopes, highlights the challenges of detecting interstellar objects against the crowded backdrop of the galactic center. The Vera C. Rubin Observatory, with its unprecedented survey capabilities, promises to change this paradigm, identifying more interstellar visitors and mapping their trajectories. Such efforts will not only refine our understanding of the Milky Way's structure, but also test theories about the frequency and distribution of interstellar comets. As 3i Atlas continues its journey, it serves as a reminder of the universe's vastness and the interconnectedness of its components. Every particle in its coma, every atom in its nucleus, is a thread in the cosmic web, linking the past to the present and the known to the unknown. To study 3i Atlas is to study the history of the galaxy itself, to trace the echoes of ancient stars and the remnants of long-dead worlds. In its silent flight, it carries the legacy of the Milky Way, and in turn, it invites us to imagine the countless other travelers that may one day cross our path. As 3i Atlas departs the inner solar system, its journey is far from over. By November 2025, the comet will have passed perihelion, its closest approach to the Sun, and will begin its slow retreat into the cold, dark reaches of interstellar space. From Earth, it will fade into obscurity, its light dimming as it moves farther from the Sun. Yet the story of 3i Atlas is not confined to the brief window of its passage. Its data, meticulously gathered by observatories and telescopes, will reverberate through the scientific community for decades, fueling new hypotheses and discoveries. The comet's departure marks the beginning of a deeper exploration, not just of 3i Atlas itself, but of the broader question of interstellar objects. Will more of these cosmic travelers be found? And what secrets will they reveal? The discovery of 3i Atlas has already challenged assumptions about the distribution of interstellar comets, suggesting that they may originate from diverse regions of the galaxy. Future missions such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time will cast a wider net, scanning the skies for faint, fast-moving objects that betray their extraterrestrial origins. With each new discovery, the map of the Milky Way's interstellar traffic will grow more detailed, painting a picture of a galaxy in constant motion. Yet 3i Atlas also raises unanswered questions. What lies beyond the thick disk, in the halo of the galaxy, or in the uncharted territories of the Magellanic Clouds? Could interstellar comets from these regions bear entirely different compositions, shaped by the unique conditions of their birthplaces? And what of the possibility that some interstellar objects are not natural phenomena at all, but artifacts of advanced civilizations? While the majority of the scientific community dismisses such speculation as premature, the mere act of contemplating it reflects the boundless curiosity that drives humanity's quest to understand the universe. As we look to the future, 3i Atlas stands as a testament to the power of observation and the enduring mystery of the cosmos. Its trajectory, like the paths of all interstellar comets, is a reminder that the universe is not static. It is a living, breathing entity, where stars are born and die, planets are scattered, and comets become ambassadors of distant worlds. In the coming years, as technology advances and our gaze extends further into the heavens, we may find that 3i Atlas is only the beginning, a single note in the symphony of interstellar exploration. And perhaps, one day, when our own probes venture beyond the solar system, they will encounter another traveler like 3i Atlas, and we will finally grasp the full scale of our cosmic neighborhood. Until then, we watch, we learn, and we wonder. Imagine a traveler from the dawn of the cosmos, a silent witness to epochs long vanished. 3i Atlas, the third interstellar object to grace our solar system, is no ordinary visitor. It carries the weight of 7 to 14 billion years, a timeline that stretches beyond the birth of our own star, the Sun, which formed a mere 4.6 billion years ago. This comet is not merely a wanderer, it is a relic of the Milky Way's earliest days, a fossilized whisper from a time when stars and planets coalesced in the primordial dark. What secrets does 3i Atlas hold? How can a single icy body, hurtling through space at 58 kilometers per second, illuminate the ancient architecture of our galaxy? Its journey is not just a passage through our neighborhood, it is a bridge to the past, a key to unlocking the mysteries of stellar nurseries and the chaotic dance of cosmic evolution. As we peer into the heart of 3i Atlas, we confront a profound question. What does it mean for an object to predate the solar system itself? The comet's existence challenges our understanding of time and space, reminding us that the universe is a vast archive of stories waiting to be told. Its trajectory, its composition, and its age are threads in a tapestry that spans billions of years, woven by forces we are only beginning to comprehend. To study 3I Atlas is to hold a fragment of the Milky Way's youth in our hands, to glimpse the raw materials from which worlds were born. The origin of 3I Atlas is etched into the fabric of its motion. By analyzing its hyperbolic trajectory and the velocity components that define its path, astronomers have deduced that this comet hails from the thick disk of the Milky Way, a region populated by ancient stars, whose origins trace back to the galaxy's formative years. Unlike the thin disk, which hosts younger, metal-rich stars like our Sun, the thick disk is a cosmic graveyard of older, more primitive stellar remnants. Stars here move in orbits tilted relative to the galactic plane, and their compositions reflect an era when supernovae had not yet enriched the interstellar medium with heavy elements. The comet's velocity components tell a compelling story. Its radial velocity, u of -51.0 kilometers per second, indicates it is moving away from the galactic center, while its vertical velocity, watts of +118.5 kilometers per second, suggests it is ascending above the galactic plane. These values place 3I Atlas in a distinct kinematic group, one that aligns with the thick disk's characteristic motions. Moreover, its retrograde inclination of 175 Dork, almost a perfect reversal of the solar system's orbital direction, further underscores its alien heritage. Such a trajectory is rare among interstellar objects, hinting at a violent past, a gravitational slingshot from a distant star system, or perhaps a collision in the crowded nurseries of the early galaxy. The comet's age, estimated at 7 to 14 billion years, is derived from the typical lifetimes of thick disk stars. These stars, forged in the Milky Way's infancy, are among the oldest in the universe. If 3I Atlas shares their lineage, it would have formed in a protoplanetary disk around a metal-poor star, where the conditions were starkly different from those in our own solar system. The absence of heavy elements in its parent star's environment would have shaped its composition, favoring simpler molecules and ices that dominate its current form. This connection to the thick disk is not merely academic. It is a direct link to the Milky Way's earliest chapters, a testament to the cosmic recycling that governs the life cycles of stars and planets. What does it mean for 3I Atlas to be a relic of the thick disk? First, consider its chemical fingerprint. The comet's coma is rich in carbon dioxide, a compound rarely seen in such abundance in solar system comets. This anomaly suggests that 3I Atlas formed far from its parent star, beyond the CO2 frost line, a region where temperatures are low enough for the gas to condense into ice. In contrast, water ice dominates comets in our own system, a reflection of their formation closer to the Sun. The presence of CO2, alongside traces of water vapor, carbon monoxide, and carbonyl sulfide, paints a picture of a comet born in a colder, more isolated environment. Such conditions are precisely what we expect in the thick disk, where star-forming regions were sparse and metallicity was low. But 3I Atlas's significance extends beyond its composition. Its survival over billions of years is a marvel in itself. Comets are fragile, their nuclei vulnerable to erosion and disintegration as they traverse the solar wind and radiation. Yet 3I Atlas has endured, its icy heart intact, thanks to the protective layers of dust and volatile ices that shield it from the harshest forces of space. This resilience raises questions about the mechanisms that allow such bodies to persist for eons. Did its parent star system provide a stable cradle, or did gravitational interactions with passing stars and nebulae scatter it into the void? Either way, its journey is a testament to the tenacity of matter in the cosmos. Perhaps most intriguing is the possibility that 3I Atlas represents a class of ancient comets that shaped the early Milky Way. If thick disk stars commonly ejected such bodies, the galaxy may be teeming with similar relics, each carrying a snapshot of its native environment. These comets could have played a role in seeding planetary systems with volatile materials, delivering the building blocks of life to nascent worlds. In this light, 3i Atlas is not an outlier, but a representative of a broader cosmic phenomenon, a reminder that the universe is a dynamic, interconnected web of influences. Yet uncertainties linger. Could 3i Atlas be even older than the thick disk itself? Some models suggest that the thick disk formed through mergers with smaller galaxies, a process that might have stirred up interstellar debris and comets from even earlier epochs. If true, 3i Atlas might predate the Milky Way's current structure, a survivor from a time when dwarf galaxies collided and reassembled the galactic core. Such a scenario would elevate the comet to the rank of a cosmological artifact, a witness to the galactic mergers that sculpted our home. To fully grasp 3i Atlas's story, we must rewind its journey to the moment of its birth. How did this comet leave its parent star system? And what forces propelled it into the interstellar void? The answers lie in the stars it has encountered along the way. As 3i Atlas traverses the Milky Way, its path intersects with the gravitational spheres of countless stars. Over the past 10 million years alone, it has passed within one past 3.3 light-years, of 25 known stars, each encounter nudging its trajectory and altering its speed. These close calls may have stripped it from the grip of its parent system, casting it into the interstellar expanse. But what of its original home? What kind of star nurtured this comet, and what fate awaits it as it continues its eternal voyage? These questions lead us to the next chapter in 3i Atlas's tale, a story of stellar companionship, gravitational chaos, and the cosmic lottery that governs the destinies of interstellar travelers. To understand its origins, we must look not only to the stars it has passed, but to the ones it might yet meet, in a universe where every encounter writes a new page in the epic of the cosmos. This structure balances scientific rigor with poetic reflection, inviting readers to contemplate the grandeur of the universe while grounding the narrative in the latest astronomical findings. Each section builds on the previous, weaving a tapestry of discovery that honors the mystery and majesty of 3i Atlas. In the vast, silent expanse of the cosmos, where stars burn like distant lanterns and galaxies swirl in endless spirals, a solitary traveler arrived. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, in Chile captured the first glimpse of 3i Atlas, a comet born beyond our solar system, hurtling through the inner solar realm on a path as ancient as the stars themselves, discovered at a staggering distance of 4.5 astronomical units (AU) from the Sun. This interstellar visitor carried with it the secrets of a distant stellar cradle, a relic from a time when the Milky Way's thick disk was young. Its arrival was not a sudden intrusion, but a continuation of an odyssey spanning billions of years, a journey etched into the fabric of interstellar space. 3i Atlas is no ordinary comet. Unlike the icy wanderers that originate from the Oort cloud or the Kuiper belt, this object arrived from the depths of the galaxy, its trajectory shaped by forces far removed from our familiar cosmic neighborhood. With a hyperbolic excess velocity of 58 kilometers per second, 36 miles per second, it races through the solar system unbound by the sun's gravity, destined to depart as swiftly as it arrived. Yet, its story is not merely one of speed and escape. It is a tale of transformation, of a frozen nucleus awakening under the sun's gaze, of a coma blooming in the vacuum of space, and of a chemical fingerprint that whispers of a home far beyond our sight. As we embark on this exploration, we are invited to witness the universe as a dynamic tapestry of motion and mystery. 3i Atlas is a messenger, a fragment of another world, offering clues about the birthplaces of stars and the chaotic nurseries where planetary systems take shape. To study it is to touch the threads of a cosmic loom, to glimpse the invisible currents that guide interstellar travelers through the void. And as we trace its path, we are reminded that we are not alone in the dark, that the stars above us are not just distant points of light, but gateways to stories waiting to be told. To comprehend 3i Atlas is to understand the laws that govern its flight. Its trajectory, a hyperbola curving sharply past the sun, is a testament to its origins beyond the gravitational embrace of our solar system. Hyperbolic orbits, unlike the closed ellipses of planets and asteroids, describe paths where objects arrive, slingshot around a massive body, and then vanish into the void. For 3I Atlas, this means its journey is finite here. Its closest approach to the Sun will occur on 29 October 2025, when it reaches a perihelion of 1.36 AU, nestled between the orbits of Earth and Mars. From there, it will retreat, its speed diminishing as it flees the Sun's pull, until it dissolves into the stellar backdrop from which it came. What propels such an object to such velocities? The answer lies in the galaxy itself. 3I Atlas's velocity relative to the Sun, 58 kilometers per second, is far greater than that of 1I Oumuamua, 26 kilometers per second, or 2I Borisov, 32 kilometers per second. Its interstellar predecessors. This suggests it has traveled farther, perhaps originating from the Milky Way's thick disk, a region populated by ancient stars whose motions are more chaotic than those in the thin disk where our solar system resides. The thick disk, a relic of the galaxy's turbulent youth, is a reservoir of stars and debris scattered by mergers and gravitational tides. If 3I Atlas hails from there, it could be over 7 billion years old, older than the solar system itself, and carries the imprint of a time when the galaxy was a denser, more violent place. Its current path, however, is not random. Though interstellar in origin, 3I Atlas's trajectory aligns remarkably with the ecliptic, the plane in which most planets orbit the Sun. This alignment is not mere coincidence. The comet's orbital inclination of 175 places it retrograde, meaning it moves in the opposite direction to the majority of solar system bodies. Such an orientation hints at a history of gravitational interactions, perhaps with stars or dense molecular clouds in its native system, that tilted its orbit into this peculiar angle. Moreover, its proximity to planets like Mars and Jupiter in the coming months offers a rare opportunity to study how even a passing interstellar object interacts with the gravitational architecture of our system. Yet 3I Atlas's significance extends beyond its path. Its physical characteristics, its nucleus, Coma, and outgassing are windows into the chemistry of distant star systems. Observations by the Hubble Space Telescope and the James Webb Space Telescope, JWST, reveal a nucleus shrouded in a coma of gas and dust, its composition dominated by carbon dioxide and water ice, with traces of carbon monoxide and carbonyl sulfide. These volatile compounds, preserved in the deep freeze of interstellar space, suggest a formation far from its parent star, beyond the CO2 frost line, where temperatures are low enough for such molecules to condense. The presence of cyanide and nickel vapor in its coma, detected by the Very Large Telescope, further underscores its alien nature, echoing the chemical diversity found in other solar system comets but amplified by the unique conditions of its birthplace. As 3I Atlas approaches perihelion, the Sun's rays will intensify its activity. Sublimation of ices will accelerate, releasing jets of gas and dust that sculpt its coma into a luminous halo. The coma's reddish hue, a signature of irradiated organic compounds, hints at a history of exposure to cosmic radiation, a journey through the galactic dark that left its mark. And yet, even as it transforms, 3I Atlas remains a fragile thing, a fleeting visitor whose existence is ephemeral in the grand scale of cosmic time. Its departure in late 2026 will mark the end of one chapter, but the data it leaves behind will echo through laboratories and observatories for generations. The study of 3I Atlas is akin to unearthing a fossil from the dawn of the galaxy. Every molecule in its coma, every grain of dust trailing behind it, is a relic of a star system we may never see. The comet's composition, particularly its unusually high ratio of carbon dioxide to water, challenges existing models of cometary chemistry. Most solar system comets exhibit a CO2 to water ratio that decreases as they approach the Sun, with water dominating the outgassing process. 3I Atlas, however, defies this pattern. Its CO2-rich coma suggests either a nucleus saturated with the compound or a mechanism that suppresses water sublimation. a mystery that could reshape our understanding of how comets form and evolve. The JWST's infrared spectrometer has revealed another layer of complexity: the presence of heavy isotopes of carbon in CO2 molecules. Isotopic ratios often serve as fingerprints of an object's origin, and the detection of carbon-13 in 3I Atlas's Coma may hint at a parent star with a metallicity distinct from the Sun. Stars in the thick disk, where 3I Atlas may have originated, tend to have lower abundances of heavy elements, a trait reflected in the comet's chemical profile. This connection between stellar population and cometary composition is a breakthrough, offering a method to trace interstellar objects to their galactic neighborhoods without direct observation of their birthplaces. Yet the comet's story is not solely written in its chemistry. Its dynamics tell tales of gravitational tides and stellar encounters. Studies by Yang Guo and collaborators suggest that 3I Atlas has passed within 1 parsec, 3.3 light-years, of 25 stars in the past 10 million years. These near misses, though distant by human standards, are intimate in the cosmic scale. Each encounter would have nudged its trajectory, altering its course through the galaxy like a leaf caught in a windstorm. The cumulative effect of these gravitational dances may have shaped its current path, accelerating it toward the solar system and leaving it with a vertical velocity component of 18.5 kilometers per second, far higher than typical for objects in the thin disk. These stellar interactions also raise questions about the comet's survival. Over billions of years, collisions with interstellar material or the gravitational pull of passing stars could have stripped away layers of its surface, exposing fresh ice and altering its outgassing behavior. The fact that 3I Atlas remains intact despite such a tumultuous journey speaks to the resilience of cometary nuclei, which are often described as dirty snowballs, held together by weak molecular bonds. Yet the comet's activity, its steady release of dust and gas, suggests that it has retained enough volatile material to sustain its transformation as it nears the Sun. This balance between erosion and preservation is a delicate one, a testament to the comet's ability to endure the rigors of interstellar travel. For planetary scientists, 3I Atlas represents a unique opportunity to compare and contrast comets from different stellar systems. While 2I Borisov, the second interstellar comet, bore similarities to solar system comets in its composition and behavior, 3I Atlas diverges in significant ways. Its CO2 dominance and the absence of certain carbon chain compounds, such as dicarbon-nition C3, highlight the diversity of materials that can arise in different protoplanetary disks. These differences may reflect variations in the temperature, density, and chemical makeup of the environments where comets form, providing a roadmap for studying the conditions that give rise to planetary systems across the galaxy. Moreover, 3I Atlas's trajectory offers insights into the distribution of interstellar objects. Its origin in the southern celestial hemisphere, opposite the solar system's direction of motion, challenges assumptions about the sources of such visitors. Previous models predicted that interstellar objects would predominantly come from the solar apex in the north, but 3I Atlas's southern provenance suggests that our detection capabilities may have been biased. Future surveys, such as those conducted by the Vera C. Rubin Observatory, may uncover more southern origin comets, revealing a hidden symmetry in the galactic distribution of interstellar debris. Even the debate surrounding 3I Atlas's identity, whether it is a natural comet or an artificial construct, adds depth to its exploration. While the majority of the scientific community dismisses the latter hypothesis, the speculation sparked by A.V. Loeb and others underscores the importance of remaining open to the unknown. The search for extraterrestrial intelligence, SETI, has long focused on signals and structures, but 3I Atlas reminds us that even the most mundane-seeming objects can challenge our understanding. Its anomalous trajectory and chemical profile may one day be reinterpreted in light of new discoveries, just as Oumuamua's cigar-like shape was initially thought to resemble a spacecraft before its cometary activity was confirmed. As 3I Atlas continues its journey, it serves as a bridge between the familiar and the enigmatic. Its passage through the solar system is a fleeting moment in cosmic time, yet it leaves an indelible mark on our understanding of the universe. The data collected by telescopes like Hubble and JWST will not only refine our models of cometary evolution, but also illuminate the broader galactic context in which such objects form and travel. This leads us to a pressing question. How does 3I Atlas compare to its interstellar predecessors? The answers lie in the contrasts and connections between these cosmic wanderers. While 1I Oumuamua and 2I Borisov offered glimpses into the diversity of interstellar objects, 3I Atlas adds a new dimension to the puzzle. Its CO₂-rich Coma, retrograde orbit, and ancient potential age paint a picture of a comet born in a different epoch and environment, one that challenges our assumptions about the homogeneity of interstellar material. In the next segment, we will delve into this comparative analysis, exploring how 3I Atlas fits into the growing catalogue of interstellar visitors and what its unique traits reveal about the Milky Way's history. Through this lens, we will see not just a single comet, but a thread woven into the vast interconnected fabric of the cosmos, a reminder that every object that crosses our path carries a story waiting to be uncovered. In the vast, dark ocean of the cosmos, where stars burn like distant lanterns and planets drift in silent orbits, a traveler arrived. Its name, 3I Atlas. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile, this interstellar comet marked itself as a rare and enigmatic guest from another star system. It is the third known interstellar object to grace our solar system, joining the ranks of 1I Oumuamua 2017 and 2I Borisov 2019. Yet, unlike its predecessors, 3I Atlas carries secrets that humankind has never encountered before. Imagine a speck of frozen chaos hurtling through the void, its nucleus cloaked in ancient ice and dust, its coma a swirling halo of volatile gases. It arrives at a speed of 58 kilometers per second, over 130,000 miles per hour, far faster than any native solar system object. Its trajectory, a hyperbolic arc, tells us it will not linger but will vanish into the abyss, leaving behind only questions. Where did it come from? What forged its strange composition? And why does it glow with a reddish hue, as if stained by the passage of eons? 3I Atlas is not merely a comet. It is a messenger. Its arrival is a reminder that we are not isolated in the universe. It whispers of distant stars, of protoplanetary disks birthing worlds, and of the chaotic dance of celestial bodies across galaxies. As we trace its path through the inner solar system, we are not just observing a fleeting visitor. We are glimpsing the architecture of the cosmos itself. When 3I Atlas was first spotted by the Atlas telescope, it was already a seasoned traveler. Located 4.5 astronomical units, AU, from the Sun over 670 million kilometers, it was deep in the outer solar system, a place where sunlight is faint and cold reigns supreme. Yet its speed betrayed its origin, 58 kilometers per second relative to the Sun, a velocity far beyond what any native solar system object could achieve. This hyperbolic excess velocity, denoted Vf, is the defining mark of an interstellar interloper. Unlike asteroids or comets born in our backyard, 3I Atlas was flung from another stellar cradle, propelled by gravitational tides or collisions in a distant system. Its orbit is a mathematical marvel. With an orbital eccentricity of 6.14, 3I Atlas's path is almost straight, a needle piercing the fabric of the solar system. For context, 1I Oumuamua's eccentricity was 1.2, and 2I Borisov's was 3.4. 3I Atlas's trajectory is retrograde, tilted 175 degrees relative to the ecliptic, the plane where most planets orbit. This means it travels in the opposite direction to the solar system's spin, a stark contrast to the orderly dance of the planets. Such a path is statistically rare, hinting at a violent origin story, perhaps a close encounter with a binary star system, or a gravitational slingshot from a massive planet in another world. By late October 2025, 3I Atlas will reach perihelion, the closest point to the Sun, at 1.36 AU 23 million kilometers, nestled between the orbits of Earth and Mars. Here the Sun's heat will awaken it fully, sublimation of its icy nucleus will release torrents of gas and dust, forming a coma that stretches thousands of kilometers. The Hubble Space Telescope estimates the nucleus to be less than 1 kilometer wide, a fragile relic of a long-lost ACOC. Yet this small core belches a wealth of volatile compounds: carbon dioxide, water vapor, carbon monoxide, and even cyanide. The James Webb Space Telescope JWST has revealed that 3I Atlas is unusually rich in CO₂, a signature unlike any solar system comet. This suggests it formed far from its parent star, beyond the CO₂ frost line, where temperatures are cold enough for the gas to freeze. What makes 3I Atlas even more intriguing is its age. If it hails from the Milky Way's thick disk, a population of ancient stars older than the solar system, it could be 7 billion years old. That is older than Earth, older than the dinosaurs, older than the formation of our sun. It is a time capsule, a fragment of a primordial era when stars were younger and the galaxy was a denser, more chaotic place. The study of 3I Atlas has united astronomers worldwide, blending ground-based observatories with cutting-edge space telescopes. From the moment it was discovered, the comet defied expectations. Early observations hinted at ambiguity. Was it an asteroid or a comet? The answer came swiftly. By July 2025, the Nordic Optical Telescope and the Canada-France-Hawaii Telescope captured its Coma, a diffuse cloud of gas and dust, confirming its cometary nature. The comet's reddish hue, reminiscent of 2I Borisov, signaled the presence of irradiated organic compounds, a fingerprint of interstellar chemistry. As 3I Atlas drew closer, its secrets unfolded. The Vera C. Rubin Observatory, in its inaugural science validation phase, imaged the comet's growing coma, revealing a nucleus shrouded in haze. Meanwhile, the Transiting Exoplanet Survey Satellite, TESS, recorded its activity as early as May 2025, when the comet was still 6.4 AU from the Sun. This suggests its volatile ices, likely CO₂ and CO sublimated, far beyond the typical water ice frost line, a phenomenon unseen in solar system comets. The JWST's infrared gaze pierced deeper. By August 2025, it mapped a carbon dioxide coma spanning 348,000 kilometers in radius, dwarfing the comet's nucleus. The data painted a picture of a body born in the frigid outskirts of another star system, where CO₂ froze into primordial snows. Yet, the comet's water ice was equally curious. Tiny, amorphous grains, likely sublimating at distances of 4,000 to 10,000 kilometers from the nucleus, hinted at a dynamic process of outgassing. Why does 3I Atlas behave differently from 2I Borisov, which followed a more familiar pattern? The answer lies in its unique chemistry, a blend of alien elements and familiar ones, as if it straddles two cosmic realms. Even its dust tells a tale. The coma's reddish tint and large dust grains suggest a history of exposure to cosmic radiation, aging the material over billions of years. The Very Large Telescope, VLT, detected cyanide, an atomic nickel vapor, gases rarely seen in such concentrations. One theory posits that nickel-containing organic compounds, perhaps nickel tetracarbonyl, decompose under space weathering, releasing the metal into the coma. Yet the absence of iron remains a puzzle. Is 3I Atlas inherently metal poor, or is its chemistry shaped by an unknown process? Perhaps the most profound question is, could life's building blocks exist in this interstellar wanderer? The detection of carbonyl sulfide, OCS, a molecule linked to prebiotic chemistry, raises tantalizing possibilities. If 3I Atlas carries organic molecules forged in a different star system, it could hint at the universality of life's ingredients. But for now, the comet remains a cryptic envoy, offering clues without answers. As 3I Atlas arcs away from the Sun, its story does not end. By November 2025, the Hubble will perform ultraviolet spectroscopy to analyze its gas emissions, while the JWST will scrutinize its sulfur-to-oxygen ratio, a window into its formation environment. Yet, even as scientists unravel its mysteries, a shadow of doubt lingers. Some voices have speculated that 3I Atlas might not be entirely natural. Avi Loeb, a prominent astrophysicist, proposed in July 2025 that the comet's trajectory, its apparent size, and its chemical anomalies could hint at an artificial origin, an alien spacecraft disguised as a comet. While this idea has sparked debate, the overwhelming consensus among astronomers is that 3I Atlas is a comet. Observations of its cometary activity, from cyanide to water vapor, align with natural processes. Still, the possibility remains. Could this be the first of many interstellar messengers, some of which might carry traces of intelligence? The truth, however, may lie in the data. As 3I Atlas fades into the void, it leaves behind a legacy of curiosity. Its journey reminds us that the universe is not a static tapestry, but a living, breathing expanse of motion and transformation. In the coming decades, future telescopes, perhaps even interstellar probes, will chase the echoes of this traveler, seeking to decode its message. Until then, 3I Atlas remains a symbol of the unknown, a beacon urging us to look beyond the stars and into the infinite. And so, as the comet vanishes from view, we are left with a single haunting thought. If 3I Atlas is a visitor from another world, what other wanderers await us in the darkness? In the vast, silent expanse of the cosmos, where time stretches into epochs and space bends under the weight of gravity, a traveler arrived. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile's Rio Hurtado, captured a fleeting signal, a faint smudge of light against the dense starfields of the Milky Way. This was no ordinary object. It was 3I Atlas, an interstellar comet hurtling through the solar system at a blistering 58 kilometers per second. Its arrival marked a cosmic milestone, the third confirmed visitor from another star system, joining the enigmatic 1I Oumuamua and 2I Borisov. Yet, unlike its predecessors, 3I Atlas carried secrets written in its icy nucleus and coma, secrets that would unravel the threads of stellar history and planetary formation. As astronomers peered deeper into the heart of this interstellar wanderer, they saw not just a comet, but a messenger from the distant past, Ampa's relic of a star system long dissolved into stardust. 3I Atlas bore the imprint of its birthplace, a place in the Milky Way's disk where time itself seemed to stretch beyond the 4.6 billion-year chronology of our solar system. To observe 3I Atlas was to witness a fragment of the universe's memory, drifting through the void to whisper its story to those who dared to listen. The discovery of 3I Atlas was a triumph of modern astronomy, a testament to humanity's ability to pierce the veil of the night sky. But how does one distinguish a cosmic traveler from the countless other objects that dance through our skies? The answer lay in its trajectory. With an orbital eccentricity of 6.141, a number so extreme that its path resembled a straight line, 3I Atlas defied the gravitational embrace of the Sun. Unlike planets and asteroids, which follow elliptical orbits, this comet was moving too fast to be bound by the solar system. Its hyperbolic excess velocity, 58 kilometers per second, was a cosmic fingerprint, a clue to its extraterrestrial origin. Yet, 3I Atlas was more than a speedster. Its coma, a luminous halo of gas and dust, revealed its true nature as an active comet. The Sun, that ancient architect of change, played a central role in shaping this phenomenon. As 3I Atlas approached, solar radiation heated its icy nucleus, triggering the sublimation of frozen volatiles. Carbon dioxide, water ice, and carbon monoxide erupted into space, carrying with them grains of dust that formed a diffuse reddish coma. Spectroscopic analysis by the James Webb Space Telescope, JWST, uncovered an astonishing truth. 3I Atlas was rich in CO₂, a composition unlike most solar system comets. This imbalance hinted at a formation far from its parent star, beyond the CO₂ frost line, where temperatures were frigid enough to preserve such compounds. But where had this comet come from? Tracing its path backward through the cosmos, astronomers determined that 3I Atlas hailed from the direction of the galactic center. More precisely, its trajectory suggested an origin in the Milky Way's thick disk, a population of ancient stars, some of which predate the solar system. Calculations placed its age at a staggering 7 to 14 billion years, making it potentially older than Earth itself. Such a timeline raised profound questions. Could 3I Atlas have formed in a protoplanetary disk that no longer exists? Had it been ejected by a long-vanished giant planet or a violent stellar encounter? These mysteries loomed like shadows over the comet's journey, waiting to be illuminated by observation and theory. The study of 3I Atlas became a race against time. As it neared perihelion, the closest point to the Sun on 29 October 2025, its activity intensified. The Hubble Space Telescope captured its Coma in exquisite detail, revealing a nucleus shrouded in dust. Estimates placed its diameter between 0.32 and 5.6 kilometers, though the true size remained elusive. Meanwhile, the JWST detected a plume of CO2 gas, extending hundreds of thousands of kilometers, a ghostly trail of the comet's volatile heart. These observations painted a picture of a fragile, dynamic world, a nucleus pockmarked with vents, spewing material into the vacuum of space, its surface sculpted by the relentless pull of solar energy. Yet 3I Atlas was not merely a passive observer of the cosmos. Its passage through the solar system offered a rare opportunity to test theories about the evolution of interstellar objects. By analyzing its trajectory, scientists determined that it had passed within 1 parsec, 3.3 light-years, of 25 stars in the past 10 million years. These encounters, though distant, could have altered its path, nudging it toward the Sun like a leaf caught in a cosmic wind. Such gravitational interactions underscored the chaotic, interconnected nature of the galaxy, a web of stars and planets where objects are born. Perhaps most intriguing was the comet's chemical fingerprint. The detection of cyanide and atomic nickel in its Coma mirrored patterns seen in solar system comets, suggesting a shared heritage of organic chemistry. Yet 3I Atlas's scarcity of carbon chain compounds, such as dicarbon C2 and tricarbon C3, set it apart. This depletion hinted at a different evolutionary history, perhaps one shaped by intense radiation or a unique chemical environment in its home system. The absence of iron vapor, despite the presence of nickel, added another layer of complexity. Was this a quirk of its formation, or a clue to the conditions in its birthplace? As debate swirled around 3I Atlas's origins, a provocative hypothesis emerged. Could it be an artifact of intelligent design, an alien spacecraft masquerading as a comet? A.V. Loeb and colleagues speculated that its trajectory aligned with the solar system's ecliptic plane, and its seemingly anomalous properties might hint at non-natural origins. Yet this claim was swiftly challenged. Observations confirmed the presence of water vapor, CO2 and other cometary signatures, aligning with the well-established behavior of icy bodies. The scientific community, ever cautious, reminded skeptics that extraordinary claims require extraordinary evidence. Still, the question lingered: how many such interstellar visitors might be misclassified, hiding in plain sight? By late 2025, 3I Atlas had reached the zenith of its journey. After a close encounter with Mars, where orbiters glimpsed its Coma at magnitude 11, the comet began its exodus from the solar system. By December 2025, it faded into the infrared haze, its final whispers captured by the JWST's sensitive instruments. Yet its legacy endured. The data it left behind, its chemical composition, its age, its trajectory, offered a glimpse into the life cycles of stars and the turbulent nurseries of planetary systems. What does 3I Atlas teach us about the universe? It reminds us that we are not alone in the cosmic dance. Every interstellar object is a thread in the tapestry of the Milky Way, a reminder that our solar system is but one node in an intricate network of worlds. And as 3I Atlas vanishes into the interstellar dark, it carries with it a promise. The next visitor may arrive tomorrow, bearing secrets yet undiscovered. Until then, we turn our eyes to the heavens, knowing that the universe is vast, and its stories are written in light. This script balances scientific detail with lyrical prose, adhering to the requested structure while emphasizing the wonder of cosmic exploration. Each section builds on the previous, transitioning smoothly, from discovery to interpretation to speculation, leaving readers with a sense of awe and curiosity about the universe. The universe, vast and indifferent, has long held humanity's gaze with its mysteries. Among these enigmas, 3i Atlas stands as a fleeting beacon, a comet born in the distant past of another star system, now careening through our own like a ghostly traveler. Its arrival in the solar system, marked by a hyperbolic trajectory and a velocity that defies the sun's gravitational embrace, stirs both scientific curiosity and existential wonder. Yet despite the allure of probing its origins, the comet remains tantalizingly out of reach. The technological hurdles of intercepting such an object are staggering, a testament to the limitations of human ambition in the face of cosmic scale. Even as we marvel at 3i Atlas's journey, we are reminded of the fragility of our own place in the cosmos. The idea of dispatching a spacecraft to meet 3i Atlas is not merely a challenge of engineering. It is a question of timing, energy, and perspective. The comet's velocity, a blistering 58 kilometers per second, relative to the sun, renders traditional launch windows obsolete. Any attempt to pursue it after its discovery in July 2025 demands a delta V, change in velocity, of at least 24 kilometers per second, a figure that dwarfs the capabilities of even the most advanced propulsion systems. Such a feat would require breakthroughs in physics and materials science, feats that remain firmly in the realm of speculative fiction. Yet the possibility of alternative strategies, such as leveraging the gravitational assist of Mars or repurposing existing orbiters, offers glimmers of hope. These ideas, though fraught with risk, embody humanity's relentless drive to bridge the gulf between Earth and the stars. Beyond the technical challenges, 3i Atlas invites reflection on our place in the galactic tapestry. As the third confirmed interstellar visitor to our solar system, it is a relic of a bygone era, a fragment of a star system that may no longer exist. Its passage through the inner solar system, culminating in a perihelion between Earth and Mars, is a reminder that the cosmos is not a static expanse but a dynamic, interconnected web. The comet's origin, whether in the thick disk of the Milky Way, where stars are ancient and metal poor, or in the chaotic dance of stellar nurseries, adds layers of intrigue. Could it carry secrets about the formation of planetary systems, or even hints of life's precursors in its icy nucleus? These questions linger as 3i Atlas continues its lonely voyage, a silent messenger from the depths of space. The pursuit of 3i Atlas is governed by the immutable laws of celestial mechanics, a domain where velocity, distance, and energy converge in precise, often unforgiving calculations. To intercept the comet, a spacecraft must match its trajectory, a task complicated by its hyperbolic orbit, unlike objects bound to the solar system, which follow elliptical paths and can be reached with careful planning. 3i Atlas is a transient visitor, destined to escape the sun's pull entirely. Its velocity, 58 kilometers per second, is nearly triple that of the fastest human-made object, the Parker Solar Probe. This speed translates to an immense kinetic energy barrier. Any spacecraft attempting to catch up must overcome this energy deficit, a challenge that current propulsion technologies cannot address. Delta V, the measure of energy required to alter a spacecraft's velocity, becomes the crux of the problem. Ampere's post-discovery mission to 3i Atlas would demand a delta V of at least 24 kilometers per second, far exceeding the 12-14 kilometers per second, achievable by chemical rockets. Even nuclear thermal propulsion, a promising but unproven technology, falls short. The numbers are daunting, but they are not insurmountable. Alternative approaches, such as launching from Mars, offer a sliver of possibility. By exploiting Mars' position relative to 3i Atlas's trajectory, a spacecraft could reduce the required delta V to approximately 5 kilometers per second. This strategy hinges on precise timing and the availability of a launch window between July and September 2025, a narrow corridor dictated by the comet's path. Yet, even this optimistic scenario faces practical obstacles. Existing Martian orbiters, such as the ExoMars Trace Gas Orbiter or NASA's Mars Reconnaissance Orbiter, lack the instrumentation to conduct a close-range study of 3I Atlas. Repurposing them for such a mission would require significant reprogramming and risk compromising their primary objectives. The role of existing spacecraft in observing 3I Atlas adds another layer to the discussion. The Juno spacecraft, orbiting Jupiter, and the Jupiter Icy Moons Explorer, JUICE, en route to the gas giant, could theoretically capture fleeting glimpses of the comet as it passes near Jupiter in March 2026. However, redirecting these spacecraft to focus on 3I Atlas would demand intricate maneuvering and consume precious fuel reserves. The Psyche mission, en route to the asteroid 16 Psyche, might also cross paths with the comet in September 2025, but its instruments are optimized for metallic bodies, not cometary science. These possibilities underscore the ingenuity required to study interstellar objects, even as they highlight the limitations of our current technological arsenal. The debate over 3I Atlas's nature as a potential extraterrestrial spacecraft, sparked by A.V. Loeb's controversial hypothesis, further complicates the narrative. While the majority of the scientific community dismisses such speculation as lacking empirical support, the idea persists as a metaphor for humanity's yearning to find meaning in the cosmos. Loeb's argument that the comet's trajectory and composition could hint at artificial origins rests on shaky ground, given the wealth of observational evidence confirming its cometary activity. Yet the controversy itself reflects a deeper truth. The study of interstellar objects forces us to confront the boundaries of our knowledge. Whether 3I Atlas is a natural phenomenon or a relic of an alien civilization, its existence challenges us to refine our tools and theories, pushing the frontier of astronomy ever outward. The inability to directly intercept 3I Atlas does not diminish its value to science. Rather, it amplifies the urgency of advancing technologies that could one day make such missions feasible. The comet's passage highlights the need for next-generation propulsion systems, such as nuclear fusion or antimatter drives, which could revolutionize interstellar travel. Concepts like the Breakthrough Starshot Initiative, which envisions laser-propelled nanoprobes reaching nearby stars within decades, offer a glimpse of what might be possible. Though these ideas remain theoretical, they are rooted in the same spirit of innovation that propelled humanity from the first rocket to the moon. 3I Atlas serves as a catalyst for such thinking, a reminder that the tools to explore the cosmos are not yet in our grasp but are within the realm of possibility. The comet's composition also underscores the importance of studying interstellar objects to understand the diversity of planetary systems. Unlike solar system comets, which originate from the Kuiper Belt or Oort cloud, 3I Atlas carries the imprint of its parent star system. Its richness in carbon dioxide, coupled with traces of water, carbon monoxide, and carbonyl sulfide, suggests a formation history distinct from the icy bodies we know. If the comet indeed hails from the thick disk of the Milky Way, its age of up to 14 billion years implies that it predates the solar system itself. Such an object could provide insights into the early conditions of the galaxy, shedding light on the processes that shaped the first generations of stars and planets. Moreover, the detection of nickel and cyanide in its coma raises intriguing questions about the chemistry of interstellar space. Are these elements common in other star systems, or do they reflect the unique history of 3I Atlas's parent star? These questions, unanswered for now, drive the quest to develop more sensitive instruments capable of analyzing cometary material at greater distances. The cultural and philosophical implications of 3I Atlas extend beyond science. Its arrival in the solar system is a humbling reminder of our cosmic insignificance. In the grand scheme of the universe, the comet is a transient visitor, a speck of dust adrift in the void. Yet, for those who study it, it is a treasure trove of information, a bridge between worlds. The effort to track its trajectory, decode its composition, and debate its origins mirrors humanity's eternal search for connection to the stars, to each other, and to the fundamental truths of existence. As 3I Atlas hurtles toward perihelion and beyond, it carries with it the weight of this quest, a silent witness to our aspirations and limitations. As 3i Atlas departs the inner solar system, its legacy is etched into the annals of astronomical history. The comet's fleeting passage has expanded our understanding of interstellar objects, revealing the dynamic nature of the cosmos and the shared heritage of planetary systems. Yet, it also underscores the vastness of the unknown. The questions it leaves unanswered will echo for generations. What other interstellar travelers await discovery in the dark reaches of space? How many of them will pass unnoticed, their stories lost to time? And what new technologies will we develop to meet them, to finally cross the chasm between worlds? These questions are not merely academic, they are the heartbeat of human curiosity. 3i Atlas has ignited a spark, a renewed determination to push the boundaries of exploration. Its journey reminds us that the universe is not a closed book, but an open invitation to learn, to dream, and to strive for the stars. As the comet fades into the distance, its influence lingers, a quiet promise that the next great discovery is always on the horizon. In the vast, uncharted expanse of the universe, where stars blaze like distant lanterns and galaxies swirl in silent symphony, a singular traveler has emerged, a fleeting whisper of interstellar origin. This traveler, 3i Atlas, is not merely a comet. It is a cosmic bridge, stitching together the fabric of our solar system with the infinite realms beyond. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, 3i Atlas arrived from the depths of interstellar space, hurtling through the solar system at a blistering speed of 58 kilometers per second. Its hyperbolic trajectory, a path too wild to be bound by the sun's gravity, marks it as a visitor from another stellar neighborhood, a relic of a star system long unseen. To witness 3i Atlas is to stand at the threshold of cosmic mystery. It is the third interstellar object confirmed to have traversed our celestial backyard, following the enigmatic 1i Oumuamua in 2017, and the mysterious 2i Borisov in 2019. Yet 3i Atlas is no ordinary interloper. Its composition, ancient origins, and unique chemical signature challenge our understanding of cometary evolution, planetary formation, and the very history of the Milky Way. As it glides silently through the inner solar system, its icy nucleus spews a coma of gas and dust, a luminous halo born of solar radiation and the secrets of its birthplace. This is a story of a comet that defies expectations, a celestial wanderer that carries the fingerprints of a distant star, from the frigid outskirts of a forgotten solar system to the heart of our own. 3i Atlas invites us to contemplate the interconnectedness of the cosmos. What tales does it tell of its origins? What lessons does it offer about the universe's grand design? As we unravel its mysteries, we step closer to answering one of humanity's oldest questions. Are we truly alone in the cosmos? Or do the stars themselves whisper of shared beginnings? 3i Atlas's journey is etched in the language of physics and chemistry, a narrative written in the movements of celestial bodies and the molecular signatures of its coma. Its hyperbolic trajectory, defined by an orbital eccentricity of 6.141, is a testament to its interstellar provenance. Unlike the elliptical paths of solar system comets, which are tethered to the sun's gravitational pull, 3i Atlas's path is a straight-line escape, propelled by a velocity of 58 kilometers per second. This speed exceeds the escape velocity of the solar system, ensuring that the comet will not return, but will instead vanish into the void, carrying its secrets back to the depths of space. The origins of 3i Atlas trace back to the Milky Way's galactic disk, a region teeming with stars, gas, and the remnants of ancient supernovae. Astronomers deduce that the comet likely hails from the thick disk, a population of stars older than the Sun and enriched with heavier elements forged in earlier epochs of the galaxy. If this hypothesis holds, 3i Atlas could be at least 7 billion years old, older than our solar system itself. Such an age places the comet among the oldest known objects in the universe, a relic from a time when the Milky Way was still young and star-forming nurseries cradled planets and comets in their infancy. The comet's chemical composition offers further clues to its cosmic heritage. Observations by the James Webb Space Telescope, JWST, and the SPHEREX mission reveal a coma unusually rich in carbon dioxide, CO2, with mixing ratios far exceeding those of solar system comets. This abundance suggests that 3I Atlas formed beyond the CO2 frost line of its parent star system, a region where temperatures are low enough for carbon dioxide to condense into ice. The presence of water ice, water vapor, carbon monoxide, and carbonyl sulfide hints at a complex history of outgassing and surface evolution. Meanwhile, the detection of cyanide gas and atomic nickel vapor by the Very Large Telescope adds a layer of intrigue, linking 3I Atlas to the volatile chemistry of other comets, while raising questions about the role of heavy elements in interstellar objects. Perhaps the most striking revelation is the comet's dynamic activity. Despite its distance from the Sun, 3I Atlas exhibits a coma spanning tens of thousands of kilometers, driven by the sublimation of volatile ices. The Hubble Space Telescope's high-resolution images capture the nucleus in stark contrast against the expanding coma, revealing a body no larger than a kilometer in diameter. This disparity underscores the fragility of comets, which are often composed of loosely bound ice and dust. As 3I Atlas approaches perihelion on 29 October 2025, its activity is expected to intensify, with dust ejection rates rivaling those of solar system comets. Yet, unlike many comets that fragment under the Sun's relentless heat, 3I Atlas remains intact, its survival a testament to the resilience of interstellar wanderers. The study of 3I Atlas is not confined to its physical properties. Its trajectory, tilted 175° relative to the ecliptic, defies the expectation that interstellar objects would arrive from the direction of the solar system's apex. This retrograde path challenges assumptions about the distribution of interstellar material and suggests that the Milky Way's gravitational tides and stellar interactions may play a more significant role in shaping the trajectories of such objects. Furthermore, the comet's passage near Mars in October 2025 presents an opportunity for planetary scientists to study its interaction with a terrestrial body, offering insights into the dynamics of cometary impacts and their potential influence on planetary atmospheres. The arrival of 3I Atlas is more than an astronomical event. It is a catalyst for reimagining the cosmos. Its existence compels us to confront the limitations of our current models of cometary evolution. Traditionally, comets are understood as remnants of the protoplanetary disk that birthed the solar system, preserved in the Kuiper belt and Oort cloud. Yet 3I Atlas, with its ancient age and interstellar origin, challenges this paradigm. It suggests that comets may not be exclusive to individual star systems, but rather part of a galactic reservoir, scattered by stellar encounters and gravitational perturbations. This realization forces a re-evaluation of how comets, and by extension, the building blocks of life, might be distributed across the Milky Way. The comet's CO2-rich composition adds another layer of complexity. In the solar system, comets typically exhibit higher water-to-CO2 ratios, with CO2 playing a secondary role. 3I Atlas, however, defies this pattern, hinting at a different evolutionary history. If its nucleus is indeed CO2-rich, it implies that the comet formed in a region where CO2 dominated over water ice, a scenario that could occur in systems with unique thermal conditions or chemical gradients. Alternatively, the high CO2 abundance might reflect a surface process, such as the shielding of water ice beneath a CO2-rich crust. Either explanation demands a revision of our understanding of how comets evolve in diverse stellar environments. Beyond chemistry, 3I Atlas invites philosophical contemplation. As it traverses the solar system, it carries the legacy of a star system we have never seen. Every particle in its coma is a messenger from a distant past, a fragment of a world that may have once hosted planets, moons, or even nascent life. The comet's age, potentially predating the solar system, raises profound questions about the timescales of planetary formation and the universality of the processes that shape worlds. Did similar comets seed the early Earth with organic molecules, catalyzing the emergence of life? Or does 3I Atlas represent a unique outlier, a cosmic anomaly that reminds us of the vast diversity of stellar systems. The debate surrounding Three-Eye Atlas's nature also underscores the human tendency to seek meaning in the unknown. When astrophysicist Avi Loeb speculated that the comet might be an extraterrestrial spacecraft, the hypothesis sparked both fascination and skepticism. While the scientific consensus quickly affirmed Three-Eye Atlas as a natural object, the episode highlights the tension between empirical rigor and imaginative inquiry. In a universe teeming with mysteries, the line between science and speculation is often blurred. Yet, even as we dismiss unverified hypotheses, the mere possibility of finding artificial signals in the cosmos keeps the flame of curiosity alive. Ultimately, Three-Eye Atlas serves as a mirror, reflecting our own curiosity and the limits of our knowledge. Its fleeting presence in the solar system is a reminder that the universe is a tapestry of interconnected stories, woven from the threads of time, space, and chance. As we track its path through the heavens, we are not merely observers, we are participants in a grand unfolding narrative, one that binds us to the stars and to each other. As Three-Eye Atlas recedes from the solar system, its luminous coma fading into the darkness, it leaves behind a trail of questions that stretch farther than the comet itself. What other interstellar wanderers drift unseen through the galaxy, their origins shrouded in the mists of time? How many of these visitors carry the seeds of life, the building blocks of worlds, or the echoes of civilizations we may never meet? The comet's departure is not an end but a beginning, a call to deepen our gaze into the cosmos and to refine the tools that allow us to answer these questions. Yet, for all its scientific significance, Three-Eye Atlas also stirs a quieter, more personal reflection. In the face of its ancient age and interstellar journey, humanity's brief existence seems both insignificant and miraculous. We are creatures of a single planet, bound to a fragile blue dot adrift in a vast, indifferent universe. And yet, it is precisely this vulnerability that fuels our yearning to understand. To study a comet like Three-Eye Atlas is to reach beyond the boundaries of our world, to grasp the threads of a cosmic story that transcends our lifetimes. Perhaps the greatest lesson of Three-Eye Atlas is not in the data it provides, but in the humility it inspires. In the grand expanse of the cosmos, where stars are born and die in cycles stretching millions of years, our species' quest for knowledge is but a flicker. And yet, this flicker is enough to illuminate the darkness, to ask the impossible questions, and to dream of answers that may lie beyond the horizon of comprehension. As the comet vanishes from view, it leaves us with a humbling truth. We are not the center of the universe, nor are we alone in its endless night. We are voyagers, explorers of the unknown, and in that pursuit, we find the essence of what it means to be human. And so the story continues, not just of Three-Eye Atlas, but of every curious soul who dares to look upward and wonder. The universe, vast and unknowable, awaits our next question, our next step, and our next leap into the infinite.